Okay, good morning, boys and girls. I hope everybody's trip to Montreal was uneventful. It's great to see all of you here. And as you know, it's the 10th annual Oscillometry seminar, and we've got a record crowd. We're at capacity by numbers. Hopefully, we actually will have, I'm almost hoping for no shows so we don't get overcrowded. And we're supposed to be maxed out for the dinner tonight as well. So just to go quickly, we know where we are. We're on the McGill campus, and we're in the Round McIntyre Medical Building, and we'll be having supper tonight at Thompson House. And it's all of a 4-minute walk away. Thank you to our sponsors, because without them, this would not be possible. It started out really as a seminar arranged around a visit by Graham Hall at the very new oscillometry unit that had been set up at the new MUHC RI. That was in 2017, and this is actually the 10th because we had 2 that year. The next one was around a conference table with Charlie, amongst other. Bruce Thompson was there, Jason Bates, and Zoltan was entertaining us with slides like this showing the near drowning Jerry Mead back in the day of working out oscillometry logistics. And then we got bigger after that and included a supper. And then finally, COVID hit, which changed the game, and all of a sudden we went hybrid. And that, well, like many things, turned out to be a silver lining in the dark cloud, because now everything's recorded, and we're a hybrid conference, and we have probably as many people online as we have in the room. So socialization, socializing, and networking is key to advancing the science. And so we have the supper and cocktail. So I hope that, like other years, we will have new projects born out of this meeting with the collaborations you guys will strike up, undoubtedly. And none of this is possible without help. So a big shout out to my students, the staff of McGill, so the staff of the MUHC, and importantly, our industrial sponsors. Thank you very much. It's very appreciated, and we hope to continue the seminar on for another decade. So with that, welcome to the seminar. We got a great program. We have 31 presentations, up from the usual 24. We have 71 institutions, 35 faculty, and we're from 6 continents. And what else do I have to say? Oh, lots of universities and lots of corporations. So everybody, let's enjoy the talks. And with that, we're going to start hopefully with Rory Chan, who should be online from Dundee. Rory, are you out there?
Hey Ron, hi. Nice to see you.
Good to see you. Ah, perfect. So is it okay if we start 2 minutes early, because our schedule is super tight and I could use the extra time?
Absolutely.
Okay, so Rory needs no introduction. We know him as a key opinion leader who's advancing oscillometry's profile in the asthma space. Rory is working hard to develop point of care metrics using oscillometry. And Rory, we're really looking forward to your talk. Take it away.
Thank you, Ron, and I hope everyone can see the slides. First of all, thanks, Ron, and also his team for inviting me to give this presentation, giving me a very precious slot. I've been given strict instructions to stick to 10 minutes, so hopefully I won't go overboard. And I hope next time I can join you in person, but I have to be very selective in terms of what conferences I attend, especially with 2 young kids at the moment. But I've been very fortunate, and I want to really present some work as part of the Oscillometry Asthma Registry, which we formed about a couple of years ago. And we've done some work, of course, with Ron and with various other people, I'm sure, in the audience as well. So I'm really just representing the group. Currently, the Oscillometry Asthma Registry is a global database or a registry comprising about 2,200 patients now, but the papers and the data that I'll be showing really pertain to the 1,400 that have stemmed from both Scotland, but also various different centres in Italy, as you can see here. The first paper that we published was on PRISM, really, and I think one of the key difficulties with trying to bring oscillometry into the limelight, and I'm sure everyone in the audience here is facing similar problems locally, is that many people want a surrogate for small airways dysfunction, whether that's the mid-expiratory flow or PRISM or whichever phenomenon you want to use. But the truth is, nothing really replaces oscillometry, which is why we're all here. But we tried to do this anyway, and we looked at PRISM, which is, of course, preserved ratio impaired spirometry in the yellow, and really looked at that group and compared it to patients who had normal spirometry and those who had obstructive airways limitation as well. And we showed a few parameters, but just for the sakes of time, just here we looked at R5-20, which of course refers to small airway resistance, and then also X5 and AX, which correspond to your low frequency and your total reactance area. And you can see here that patients with PRISM do in fact have worse small airways dysfunction parameters compared to patients who have normal spirometry. So I suppose if in the absence of oscillometry, one could potentially use PRISM as a metric for predicting SAD, although it's not ideal. More recently, we published this paper in ERJ showing that patients with higher BMIs generally have worse oscillometry parameters, but not spirometry, funnily enough. And you can see in the top two graphs, the spline regression graphs, that your FEV1 and your FEV1 to FVC ratio are relatively static. And although there are two slopes near the ends of the BMI cut points, the proportions of patients were quite small with BMIs of 15 or 50 or beyond. So I think we can probably ignore those for the time being. But when you look at the center of the graphs, you can see FEV1 and the ratio are generally quite static. But when it comes to the R5-20, the R5-20 divided by R5, so that's the ratio between the small area resistance to the total area resistance, as well as X5 and AX, they all seem to have a very convincing slope. So the main learning point from this paper was that BMI, as we already know, does have a significant impact on your oscillometry parameters. But not only that, but we also did a mediation analysis after that and showed that obesity seems to be contributing about 26 to about 40% of the association between your SAD and your exacerbations. So that was another interesting outcome from this specific study. The last published study that I want to show is another paper where we looked at the combination of both spirometry and oscillometry, and maybe to make it a bit more palatable to our non-oscillometry colleagues, but instead of saying, oh, we're going to replace spirometry with oscillometry, which is my hope, obviously, often I say, why don't we combine spirometry and oscillometry and do both and see if it makes a difference? And you can see here we use that R5-20 divided by R5 ratio, but also your FEV1 to FVC ratio to divide patients into four groups. And your group 4 basically in the top left depicts patients who have airway obstruction, but also an elevated small airway resistance ratio indicative of SAD. And you can see here using binary logistic regression that patients in group 4 actually had the highest exacerbation frequency compared to groups 1, 2, and 3, both for 1 and 2 exacerbations in the different groups. What hasn't been published yet is this specific paper where we are currently basically trying to predict exacerbation frequency using different phenotypes. And ultimately, we split the cohort into 4 different different phenotypes, namely your R5-20, your FEV1, your pheno, your blood eosinophil count. The reference group were patients who didn't have any elevation or abnormality in values. And then you've got single groups who had one abnormal parameter, dual groups, triple, and then quadruple. And basically, the overall pattern that we saw was that if your eosinophils were raised, but everything else was normal, then your adjusted odds ratio for an exacerbation was 1.65, which is elevated. If you add on pheno, as we know from Oracle and other studies, then your risk does increase, and that goes to 3.06 for one exacerbation, as you can see. And then if you add in FEV1 and then R5-20, the risk progressively increases. So the more risk factors you have, so-called to speak, the greater your risk of exacerbations. And that held true for both 1 and 2 exacerbations. But what I didn't tell you from that specific table was because you're comparing to the reference group, which had 0 elevated risk factors or phenotypes. But what it doesn't tell you is what happens when you compare the quadruple group, which is the quadruple with either AX or R5-20 versus the standard one that we use in asthma, which is blood eosinophil counts and FeNO. And you can see again that when you compare 4 versus 2, it is indeed again showing that 4 risk factors are more risky in terms of exacerbations compared to 2. So I'll finish off here, but at the moment we have 2,200 patients across Scotland, Italy, and Belgium, and hopefully we continue to increase. It's currently unfunded, although we're trying to get some funding to support the activities that we're doing. So anyone with any oscillometry and clinical data are very welcome to join. So thank you for listening, and I'd be happy to take any questions.
Thank you, Rory. And just to reiterate, it's a mountain of work that you've accomplished. And to get together so many people at the international level to collaborate is really a huge accomplishment. You're to be congratulated. I'll open the floor. Does anybody have questions for Rory? Charlie.
Rory, excellent presentation. I'm really intrigued by PRISM because in the lead study, we also see that with PRISM have a marked fall in lung function over a fairly short period of time. So what about PRISM, which is basically a loss of lung volume? Why are they in particular mind so much more likely to have worse asthma or exacerbation?
Yeah, it's a really good question. I suppose when it comes to Prism, what we're trying to say is that the ratio is maintained. So that could also be relating to the FEV1 dropping, but also the FEC dropping as well. So you're falsely maintaining the ratio. And we know with a lower FEC that in some cases can relate to air trapping. Now, of course, that's just a hypothesis, but I suppose if you've got more air trapping, then by definition, we have more small airways dysfunction. And like you correctly said, it can increase the risk of longitudinal lung function decline. Although in both in asthma and in COPD, there's very little data to suggest that, SAD can lead to longitudinal lung function decline. And that's something that we definitely need to work on as part of all our international efforts, as Ron mentioned. But there is some data.
Keep in mind that FEV1 is driven by it's the volume you get out in a second. Smaller volume, and that would account for why the ratio is.
I agree. I think the FEV1 can be maintained, but I suppose the FEC can also be reduced. So there's kind of 2 ways to maintain the ratio.
Well, the one needs to be.
Ron, can I ask a question?
Jason, hop in. Welcome.
Yeah. Hi, Rory.
First of all, how are you feeling?
Just a mild case of bubonic plague. I'm doing okay.
You look remarkably well, but please stay away. We appreciate your absence.
I feel like shit, but anyway, that's good. No, I'm glad I'm not up there infecting you. So yeah, you said that air trapping is by definition small airway disease, small airway dysfunction, and I guess I've always been a little bit puzzled as to what exactly the definition of small airway dysfunction is. But you can have air trapping through the formation of liquid plugs in the small airways. So the airways may be structurally and functionally normal, but they have extra secretion, so you get mucus plugs. Do you consider that small airway disease as well?
Thanks, Jason. Yeah, so I think I'd be very keen to hear what Ron feels as well. But I think to me, small airways dysfunction encompasses clinical, functional, as you said, but also physiological changes, and that would include your small airway remodeling features, which we know from Eileen Sie's very recent nice paper published in Blue that includes mucus plugging as well. So yeah, you're right. I think with small airway obstruction, you would expect air trapping as well.
Okay, thanks.
Yeah, I know back in the day, Jason, when we were much younger, we were talking about the small airways disease based on structure function. And I guess our mind was bent around the histology that we were seeing. I like the term dysfunction better than disease for the D of SAD, because I think it's more all encompassing, which would include these transients that you're talking about, because on some days those airways will be occluded with mucus or liquid and collapse. And other days they'll be open and functional. And they may not appear diseased at all. For me, the disease is a little bit more of a permanent thing, but these are nuances, and I'd be interested to hear what other people think as well. Does anybody else want to jump in on this theme, or shall we move on to the next question? Eric?
Not a question, but I can.
Okay.
In the mucus plug world, in COPD.
Identify yourself, Larry, because the others online can't see you. This is Larry Lands.
Okay. For those who have permanent opposed to transient, they do worse. So there's a difference between having a plug today and having a plug
Always.
Oh.
Eric, did you
Yeah,
want to
just
say
a
something?
question about the registry. You know, even though it predicts exacerbation, some of the data. Eric Garshik, by the way, from Boston.
Thanks.
Right, sorry. How do people get in a registry? Are these a group of sick people to begin with, or not sick?
Great question. So all patients are being seen by a secondary care physician. So by definition, they're sick, but they are stable. So they're not necessarily having acute exacerbation. We're doing oscillometry, but they've come to clinic with moderate to severe asthma. Perhaps it's uncontrolled by definition using, like a symptom score like ACT or ACQ, but they're not actively exacerbating. So that's why they're in the registry.
Thank you.
Sam, did you have a question?
Yeah, thanks for a great talk. I'm curious to know if you also see a subset of subjects who have abnormal spirometry but normal oscillometry, and what is your take on that phenotype?
Yeah, great question. Thank you. Yeah, I think that's probably the most puzzling group, to be honest, and I'd love to hear your thoughts as well. We were thinking whether that relates to largely proximal airway dysfunction or some type of excessive dynamic airway collapse. Although I think obviously oscillometry isn't the gold standard to assess for that. It is one of the challenges of assessing both oscillometry and spirometry at the moment.
Yeah, I agree. I think that the maneuvers is radically different, so I would advocate to maintain both spirometry and oscillometry rather than placing spirometry and oscillometry. I think they're very complementary.
Yeah.
Leonard.
Leonard Blumblad. Yeah, I'm also puzzled by this group. And many years ago, a former colleague and I, we went through a few articles where they had done both, and we found that there was really a small group of people who had, significant changes in spirometry, but not oscillometry. I think we ended up like 4 or 5% in some of that range. We were so puzzled by this, of course. I think at the end, after discussing with other people, we agreed that maybe it's a question of lung volume, that some people just have higher mean lung volume while doing oscillometry, which would sort of counteract some of the impedance changes you would see by disease. That would be at least a logical explanation for why the signal would go away. Yeah, I think it's about that.
I would encourage anybody who's got large data sets to look at it. In my own, about 20% of the time, I get a discord between spirometry and oscillometry. And when they agree, we feel great. But frankly, the fun is where they disagree. Because there we're going to make new observations, because we're just feeling the elephant at different parts of the body, essentially, as we blindly go forward deploying oscillometry. And one technology is saying, how fast do you empty your lungs, which is a different question from how even are the mechanics of your lung. And I think if you approach it that way, we may reveal new phenotypes that we haven't appreciated to date, which will help us go forward with precision medicine.
Yeah, around.
Charlie, let me just take one more from Colorado, and then I'll circle back to you.
Yes, Brad Smith, Colorado. So we've experimentally seen normal oscillometry in rats and seen abnormal forced expiratory maneuvers, which are like rodent version of spirometry, where you just suck the gas out instead of having them blow out because they're very uncooperative. And in that case, we dove into the structure, and it was a loss of airway parenchymal tethering. So we were seeing normal airways mechanics with the oscillations, but dynamic collapse with the spirometry.
I'll ask out of ignorance because the rat airway tree is more like a coniferous tree rather than a deciduous tree in terms of its branching. And how much does that change the mechanics at the level of, say, oscillometry? Does anybody know the answer to the question? My Meekins days are too far behind me to remember because we mechanically ventilated hundreds of rats in the day, but I never really thought to ask that question.
Looking at me.
Okay, I'm looking at you. You're my mentor.
My mind had wandered, so tell me the question.
The question was, do the mechanics of a rat airway, which is essentially a coniferous tree type of branching approach, differ from that of other mammals, which have more of a deciduous tree branch?
Yeah, it does. I mean, mice and rats have massively huge airways. I mean, they're really, really. It's one of the reasons you don't see, like in mice, for instance, where I have a lot of it. You don't see much change in airways resistance. It's all in sort of air traffic, and these data I did with Jason. The branching structures markedly different. So they're very, very different.
Yeah, I have unaware of the modeling folks. Whereas Jeff actually trying the rat airway as opposed to the traditional airway.
Yeah, did measure rats long ago. They're pretty nonlinear doing oscillometry because with amplitude, you vary the amplitude. I mean, I think it's more a point of what you're doing. If you're sucking the air out of the animal, elastic recoil is going to be very, very important. So the tethering and oscillometry, I'm not sure what Brad, they might have had a little peep, so a little bit of pressure when they're doing oscillometry. Otherwise, when they're doing the inverse of oscillometry, there should be also some sucking out of the lung and squishing it down. There's some old data that Jason did with Gail Deckman that definitely showed as you go to very long volumes, and that was dogs, you can collapse lots of the lung with zero peep, right? So you generally use a little bit of extra peep in oscillometry, but obviously there's no peep when you're sucking the air out. So I think that's the major difference in those particular measurements. And tethering is tethering, whether it's a coniferous tree or a deciduous.
So we did run those at peep 0 too, and it was also quite similar, but I think with the forced expirations, like profoundly negative, you know.
One last question, and then we'll move on because we're 1 minute away.
Natalia from Kids.
Louder?
Yeah.
Natalia?
Yes, Natalia. And I saw exactly that with 3 patients in PEDS, that they have bronchomalacia. They have abnormal, because they have like forced maneuver, normal spirometry, but normal oscillometry.
So
bronchomalacia.
So what's it going to look like in bronchomalacia? This is more of an upper airway dysfunction, but I don't know if the mic's picking me up. If you have a shunt effect where you have a compliance, a resistance, and a compliance, you're going to get a frequency dependence of resistance the same way we're going to see with peripheral small airways disease. And this is one of the big bugaboos in oscillometry, giving you false positive results. Not only the very obese, but the people who may have trichomalacia. But I haven't seen real cases in my practice to say that is real. This is more theoretical. Maybe some of the other people who have had experience with trichomalacia might actually tell us or share with us what they've seen. Anybody? Did I answer your question?
Yes, it was more like I have seen normal oscillometry, normal spirometry in patients that they have bronchomalacia. It's more distal stimulation.
Okay.
The upper airway and the oscillometry is completely normal. But whenever they force the maneuver, it's actually when you see the abnormal spirometry, but the oscillometry is normal.
I'd love it if you could share those cases. The traditional PF. So thank you for that. Okay, So we're now going to thank you, Rory, very much. That was a great talk as usual.
Thanks, Rob. Thanks, everyone.
And now I have the pleasure of welcoming from McMaster, Alex Matheson. And let me get you on full screen. Oh, we got to go back to share screen too, don't we? Where's my means? Boom. Here you are. And hopefully. Are we good? Pointer here if you need it.
Okay, thank you very much. So good morning, everyone. I'm Alex Matheson coming here from McMaster University, and a bit of a different background here. I'm an imaging scientist. My background is coming in from physics, a lot of MRI reconstruction, stuff like that. And so what I'm going to be talking about today is really continuing on with this theme of comparison between functional techniques. So yes, looking at spirometry and oscillometry, but also adding in xenon MRI to the mix as another way to assess lung function. So we're looking at this specifically in asthma today. We're all familiar with the physiology, but what this allows us to do is really look at the comparisons and contributions of some different pieces in terms of airway hyperresponsiveness, airway wall thickening, mucus hypersecretion, all of this and how it plays into the functional context in asthma. So for those of you who aren't familiar with the imaging side of things, I'm an MR scientist. So what we look at in our lab is hyperpolarized xenon MRI. So this would be our setup here with a 3T scanner and the xenon coil that we've got attached. If you were to do a traditional sort of structural MRI, you don't usually get a lot out of the lung just due to the low proton density. So that's why we've taken to using hyperpolarization. So we use a piece of equipment called a hyperpolarizer, which produces magnetized xenon 129 gas, which we can then transfer to a dose bag and have participants inhale it in the scanner to give us a visualization of lung function by looking at where xenon goes as a surrogate for lung ventilation. So you'll see the large black lung segment there in the upper lobe. And this would be what we would call a ventilation defect, which then we measure with the ventilation defect percent, or essentially the percentage of the lung that's not being ventilated by xenon. So some recent publications have established an upper limit of normal here for VDP of 2.5% that we'll be using for this presentation. So we've got a number of techniques that we can really use to get at lung function. We're familiar with spirometry, we're familiar with oscillometry, and now we've got xenon as well. But there's some key differences between these techniques in terms of maneuver. So we've got spirometry, which is a dynamic expiratory maneuver. We've got oscillometry, a free breathing maneuver, but xenon's different. It's a inhalatory maneuver. So we're inhaling forcefully the xenon gas and then at breath hold performing imaging. So with this in mind, we might expect some differences. We've also got differences in terms of sensitivity to small airways. With xenon, we have the benefit that we know for certain we can see out down to the alveolar level. Doesn't mean we can resolve them, but our signal is really dependent on what's going on at the alveolar level. Oscillometry, of course, we're getting that extra biomechanical information. We don't get that out of imaging. So the hope is with all of this, we can really get a marriage of different expertise. So the question we're looking at here is, do all of these measurements agree? And if not, what's the prevalence of this disagreement? And can this disagreement help us better understand what's going on in the lung? So if we go back to spirometry, we can actually think of what's going on here in terms of a space looking at both flow and volume. So when we're looking at spirometry, we're really looking at integration over certain areas in terms of FEV1 or FEF. But if we're looking at oscillometry in terms of flow volume space, we're really occupying a different region. And then imaging is taking a completely different piece altogether. This is an integration. We're really looking at one particular point on the flow volume curve, though we suspect this is being influenced by the inhalatory path we're taking to get here. And going back to Ron's analogy, we really are looking at an elephant from a few different ways here. The hope is imaging is giving us a bit more. So in order to look at this, I did a retrospective analysis of our severe asthma patients that we've imaged at the Firestone Clinic over the last 5 years. So we have a little over 100, but in terms of getting everybody with all 3 sets of measurements, we're down to about 69 total with paired both pre and post bronchodilation measurements. So just looking at this cohort very briefly, these are indeed severe asthma, very poor control, poor quality of life, and a number of these individuals very eosinophilic and have high mucus burden as well. So in the imaging literature, we've really been focused on just establishing correlation between a lot of these various measurements. Of course, very important when setting yourself up in the field and marrying ourselves to gold standard measurements. But we've kind of left it at that. We've said that there are indeed relationships with FEV1, oscillometry, and VDP. But when we actually start looking at them, and this is data from this cohort, you can see that, yes, we've got some nice linear relationships, but if you look at a regression coefficient, for instance, we're really not capturing a lot of that shared variation. So there's some agreement, but these certainly don't appear to be measuring the exact same thing. If we look, for instance, at AX coming from oscillometry, you're getting a much better relationship with what you see with spirometry. So let's look into actually some ways of quantifying this disagreement. So the simplest way to start off with this was looking at some Venn diagrams. And so what we're doing here is categorizing patients based on normal versus abnormal spirometry, oscillometry, and MRI. So with spirometry, we're looking at both ratio and FEV1 Z-score. Again, we're trying to be a bit liberal here. Oscillometry, we were looking here at both AX, R5, MRI, looking at VDP. So pre-bronchodilators, some of the things that stand out here is nobody is an orphan. None of them are abnormal on just one measurement alone. But there are still about 20% that are abnormal on 2 out of your 3 techniques. And our largest subgroup here is interesting of both spirometry and oscillometry abnormal, where we're not seeing a match with any sort of ventilation defects. Now, things get more interesting if we move to a post-bronchodilator setting. So in this case now, we've gone from about 80% agreement down to 50% agreement. So of all of these patients with asthma, only half of them are showing abnormal across all of these different ways of measuring lung function. And we've actually got some sort of larger groups starting to pop through here. Though interestingly, again, there's only one participant here who's abnormal on oscillometry alone, but not the other techniques. Though also interesting, we've got quite a large group, so about a fifth of the patients that are abnormal on both spirometry and MRI, but we're not seeing abnormalities on oscillometry. So again, quite a bit of disagreement here. And so just to show that this isn't always clear movement either, this is a Sankey plot showing where these particular patient groups are moving. So you can see of those abnormal patients, about half of them stay abnormal across measurements post-bronchodilator, but then there's a real redistribution between these different groups in terms of how measurements are progressing post-bronchodilator. So we'll look at a couple examples here in a second. Now, this may be a bit of a simplistic way to look at it in terms of just normal, abnormal, and these lumping of variables together. So here's a more detailed way of looking at it. So if you've not seen one of these before, this is an upset plot. So the way to read this, we've got our histogram at top showing these different groups that we can look at and ways of breaking the data down. And below it, any of the filled circles indicate that there's an abnormal measurement for that variable. So pre-bronchodilator, our largest group at 29 participants here out of our total of 69 had abnormal measurements across all our measurements we looked at: spirometry, oscillometry, and imaging. Though interestingly, our second largest group here, abnormal in everything except R5, which might be a little counterintuitive here. But things really get much more interesting again post-bronchodilator, where you can see things are starting to spread out a lot more, that we're getting a lot more groups where there's some disagreement here. So our largest group is still that we're abnormal across all of these measurements, but we've got this second group here where we're just seeing an abnormal ratio and abnormal VDP, but none of their oscillometry measurements are abnormal. Likewise, their FEV1 is normal. So we're starting to see some of these different, I hesitate to call them phenotypes, but some different groupings popping out. So let's look at some examples. We'll start with an easy one here. This is a patient, again, severe asthma, very poor control, mixed eosinophilia, neutrophilia, and very poor lung images. So just looking at them, you can instantly see that this is somebody who's very sick. So if we look at both pre and then their post-bronchodilator, again, abnormal across their measurements, some improvement in spirometry and some very small improvement in imaging between pre and post-bronchodilator, but very little movement here in oscillometry. Now let's look at a bit of a different case. So this is a group that are starting off that they have completely, with this patient, abnormal measurements across the board here. But then if we're looking post-bronchodilator, Looking at imaging, it looks like we've seen no change. Patient very much the same. If anything, their VDP is increasing. And again, some improvement in spirometry, but importantly, still an abnormal ratio. But looking at some oscillometry measures here, quite a big change, a lot of normalization. And then again, another example here of disagreement, an image showing that we've got some very large pervasive defects across the lung, some cases whole segments knocked out. Again, very eosinophilic here. But then if we're looking at them following bronchodilator, a lot of improvements, normal spirometry now, normal oscillometry, but still some abnormalities in imaging. Looking at those images, you would not mistake them for a healthy person. So again, this is a bit surface level. We're of course limited in time, but what I'm hoping to impress upon you is that spirometry, oscillometry, and now when we add imaging to this, it gets even more tangled up, confusing. We've got a lot of disagreement here. And this disagreement is really exacerbated when we look at imaging post-bronchodilator. And I think this is, of course, hopeful. If we've got 3 techniques that are all different ways of measuring spirometry, we would never use all 3. But the hope is that by adding together these different pieces, they're going to give us a more complete picture of what's going on physiologically. So we've got some hypotheses now about what might be causing these discordances and what these different groups might represent, but we really need to start digging into our data more in terms of looking at some of our CT data for mucus occlusions, and trying to better understand how the different maneuvers that we're using in these techniques may be affecting our outcomes. For instance, if the deep inhalation we're using in xenon might be triggering some deep inhalation physiology. So these are some of the folks that have helped out with this research over the years, and thank you for letting me present here.
Well, spectacular. You all know that I'm a big fan of the functional imaging. You've given us a lot of data. You've given us a lot to think about, potentially new phenotypes. And the fun is going to be, are we seeing, what are the mechanisms behind your observations? There is no way we're going to pack that into the next 10 minutes. So what I encourage people is over coffee and supper, let's talk about this a lot more. Very exciting. So that's my comment. Are there questions?
Yeah, Ron, this is Kim in San Diego.
Okay, Kim, go ahead. Jump on in.
Thank you.
How are you doing?
I'm good. I'm doing well. Thank you. I sound better than Jason at the moment. Unfortunate for you, Jason. I guess this is a sort of a top level question about apples and oranges. I feel like this talk brings up the topic of we're looking at different things. And, you know, if you plug off an airway, that airway's not contributing to the world or to the lung in a sense. And that's what VDP sort of gets at. And to that extent, I would sort of encourage you for discussion to think about a stupid thought experiment. And I seem to do these stupid thought experiments at times. What would happen if you just clamped the main stem bronchus? Stuck it there, you put a clamp on it. What would happen to your spirometry? What would happen to your oscillometry? And what would happen to VDP? And I realize that's an extreme and somewhat stupid experiment, but sometimes those are insightful. So I don't expect that to be answered right now, but I just sort of toss it into the mix. So thanks very much. And Bron, as ever, thank you for doing this seminar. It's always wonderful. Thanks.
I appreciate the comment, and that's the starting point. Then your clamp, you're going to migrate distally generation by generation to answer your question. So no question is ever stupid. I think that's actually a good thought. I'm going to let Sam, who's going to ask a question, give his 2 cents worth before I make one more comment. On your slide of the full volume loop, you're actually not going up to TLC, but you're going up to FRC plus 1 liter, if I know your technique.
Yes.
So the dot should be moved a little bit.
Yeah.
But the point is well taken. I really like the clarity with which you put together these different modalities. I think it's helped a lot of us who are grappling with this understand it better. And certainly your command of data visualization is really impressive. Okay, Sam.
Yeah, thanks. Sam Bayard, Grenoble, France. So very thought-provoking data. And I had a sort of an extension to what Kim just said. So oscillometry is a tidal breathing method. You're round, as you very nicely showed. So for the sake of argument, I'll say that I'm a fan of xenon, and my experience has been, if you do a single static xenon image, it is much less sensitive than doing a multiple inhalation xenon and looking at the time constant of the xenon wash-in. I understand that technically it's very costly to do that with MRI, but for the sake of argument, I'll say, what if instead of doing a single static inhale and image the lung at close to CPT, that you would try a multiple breath wash in and analyze that? Do you think it would compare better to at least to oscillometry? Spirometry is a different story, but
I think there would be some differences there. And one kind of hint with all of this is, yes, we've got Xenon. I'm a Xenon fan. It's a great technique, but there's also now a community working with more traditional MRI, some of the very modern sequences, and doing techniques such as matrix pencil MR and something called pre-full, which is gaining a lot of popularity, where we are taking dynamic images and free breathing over time and then using image processing software to get deformation maps out of this and get other surrogates for ventilation. So we've seen on imaging when we're comparing these sort of free breathing proton techniques with what we're getting with Xenon, that there is some alignment. In COPD, for instance, areas of emphysema match very well, which again, you would expect if you've got damage in the parenchyma. But when we're looking at things like asthma, we're seeing a lot more discordance. So that might point to that same idea of free breathing versus an inhalatory maneuver.
yeah, just for the sake of argument, I'll just say that pre-full is maybe an estimate of ventilation, but it's not the same thing as having a tracer gap.
Yeah, agreed.
Which would be truly a true ventilation.
Yeah, well, we were talking yesterday, Sam and Alex, and I have been grappling along with Maxime and Danielle, two of the students, data from your group, which looks at the specific ventilation, which is kind of a pre-file done in the tidal breathing range, comparing that to Xenon, which is the FRC plus 1 liter. And the interesting thing is the spirometry is correlating very nicely with the Xenon, but it's the oscillometry, and in particular the intra-breath oscillometry, that's giving us the signal with the specific ventilation. And so mechanistically trying to understand, are we seeing a lung volume range effect between the two techniques? Is the best we've come up with so far after polling many people, but I'm going to take advantage of being at the podium to poll the room. Does anybody have thoughts on that issue to help Alex, Daniel, and Maxime write their manuscript? Jeff.
Do I have thoughts on that issue? Well, I think pre-full is actually really great technique, and I actually would disagree a little bit with Sam, is that it's actually ventilation because you are breathing, right? And Xenon MRIs at a different time span, inhaling 20 seconds, well, it's inhaling quickly, and then sitting there for 20 seconds while the gas diffuses, exploring longer time constants. I think is something related to the discordance, right? Or the concordance, because I think imaging was in agreement with spirometry. Actually, spirometry is an interesting one because we actually take a while to go through and measure the whole spirometry. So it's at a little different time scale than oscillometry, which is during breathing. I think thinking about the time scale of your measurements is actually a pretty useful way of maybe looking link or discord your pulse.
Okay, we'll take one more comment from Charlie and then move on.
Well, as a physiologist, I think we fail to understand real. We want these things to agree, right? Because then we're all happy. We can go home. So, what they don't, and they should. And they're all three are done with different maneuvers, and Jeff just pointed out the time domain, but there's also the volume domain, what lung volume they're being done, whether they're being done forced or not forced. And I think during normal breathing, you have the effects of neural innervation of airways, for instance, which disappears when you take a big breath. So all these things, it's a surprise, I think, how well they correlate in disease, because I think it's because the lung is basically particularly in the kinds of patients you're looking.
Yeah.
Because National Jewish, we had the same kind. They're just a mess. It kind of doesn't matter what you measure, you're going to find out. It's in the normal population where it's interesting. And I think one of the things we're seeing in the LEAD study, for instance, I'm sorry, in the lung health cohort study, where we're doing CT scan in 4,000 people between 25 and 35, and a surprising number of abnormalities, beyond just solitary nodules, which is what you expect. So I think without a lot of normal data in normal people, which would be frightfully expensive, it's sometimes very hard to understand what these things.
And we do have more normal coming. We've got the CanMuck study now that a number of sites, folks in this room are starting up.
Yeah.
Where hopefully we'll have a few hundred then normative data points that will be
going to help a lot.
Okay, thank you very much, Alex. So I'm very pleased to introduce Rachel to you, who is now in third-year medical school. She joined the lab late last summer and said, despite the end of the summer, I want a project. And so we gave her some data coming from CMONC-BR in Sherbrooke that they were struggling with. And I let you judge as to how well Rachel has sorted all of this out. The podium is yours.
Hello, everyone. Well, I don't have to introduce myself. Thank you, Ron, for the introduction. So I'm an incoming third-year medical student. I have the pleasure of presenting my project, which is exploring the relationship between inflammatory phenotype and response to systemic corticosteroids using respiratory oscillometry. And this work was done in collaboration with Dr. Couillard and Dr. Celis Preciado and their team over at Sherbrooke University. Specifically, we're conducting a post hoc analysis of oscillometry data from the PRISMA study, which is the phenotyping the response to systemic corticosteroids in the management of asthma attacks. So before getting into our oscillometry analysis, I'll start by briefly introducing the clinical problem that motivated PRISMA. So ultimately, asthma attacks are heterogeneous, they're very common, but their treatment remains mostly uniform. So as many of you know, asthma is a very common chronic respiratory disease. It affects approximately 400 million people worldwide. And a major feature of asthma is the occurrence of these asthma exacerbations, which are defined by worsening symptoms and or a deterioration from baseline lung function. And these are associated with morbidity, healthcare utilization, and avoidable deaths. Despite this burden, the acute treatment of asthma has actually not changed substantially in the last decades, and it follows this one-size-fits-all approach where most patients experiencing an asthma attack receive a course of oral corticosteroids with the ultimate goal of reducing their relapse and their hospital admission rates. But this is different from what's happening in chronic asthma management, where the field is increasingly moving towards a treatable traits approach, where treatment can be guided by specific clinical and biological characteristics that help identify patients who are at higher risk. And this is very useful because it allows to identify those high-risk patients, avoid unnecessary treatments, and etc. And a major example of this treatable traits approach is type 2 inflammation. So characterizing patients with a high inflammatory burden to then do anti-inflammatory therapy using blood eosinophil count and the fractional exhaled nitric oxide test. So PRISMA aims to apply this personalized medicine, but to acute asthma management. And the study of PRISMA asked whether inflammatory phenotype during an asthma attack could help predict the physiological response to corticosteroids. And our analysis was using the oscillometry data from the PRISMA study. So I'll just quickly overview the study design. So it was an observational study, and patients were enrolled during a severe asthma attack. On day 0, there was multimodal phenotyping, and on day 7, so before and after a 7-day course of oral corticosteroids. And what's important for our purposes is that pre and post bronchodilator spirometry and oscillometry were taken on visit 1 and visit 2, so day 0 and day 7. So this brings us to PRISMA's main finding, which was that T2 status, or the inflammatory burden, predicted objective FEV1 response. So that was their key result. Moving on, I don't think I need to go over any oscillometry. Speaking to a room of experts, so I'll swiftly move on. And now to our objectives. So our post hoc question was, does T2 inflammatory burden track with oscillometry? So the original PRISMA study showed a clear graded relationship between inflammatory burden and an improvement in FEV1 after the oral corticosteroids. However, FEV1 is a spirometry measure. It only captures one aspect of lung function and may not fully reflect small airway dysfunction, which oscillometry is particularly well suited to detect. So using the PRISMA dataset, our aim was therefore to determine whether oscillometric indices were associated with this T2 inflammatory status and to characterize how these parameters changed following the 7-day course of corticosteroids. And our hypothesis was that T2 high attacks would show greater small airway abnormality at baseline and a stronger physiological response to prednisone. So here are our methods. Our data set included 52 patients. And again, oscillometry data was taken on day 0 before the 7-day course of prednisone and after the 7-day course of prednisone, both pre and post bronchodilator. And we used the same blood eosinophil count and fractional exhaled nitric oxide cutoffs for our T2 low, T2 mid, and T2 high groups, which reflect the inflammatory burden of the patients. And then we compared oscillometry parameters across these 3 ordered inflammatory groups, and we did some trend tests. So here are our results. So turning to our first result, we examined baseline AX percent predicted on day 0, so before any corticosteroids were administered. And as a reminder, AX is the area of reactance, and higher values are reflecting greater small airway abnormality and a greater impairment in respiratory mechanics. So AX percent predicted was calculated using the Berger reference equation, and here is the clear stepwise increase across the T2 groups. So median AX percent predicted was 282 in our T2 low group, 432 in our T2 mid group, and almost 900, so 895 in our T2 high group, and this was statistically significant. So overall, greater T2 inflammatory burden was associated with more pronounced baseline small airway dysfunction during the asthma attack. This suggests that the biomarker-defined phenotype was not limited to differences in blood eosinophils and the FeNO, but was also reflected in measurable differences in airway mechanics on oscillometry. The second main result is that oscillometry also captured a corticosteroid-related response. So here we focused on the change in post-bronchodilator R5 from day 0 to day 7. And R5, of course, is a measure of respiratory resistance and is generally, We again observed an ordered pattern across the T2 groups, and the trend was statistically significant. So the T2 high group with the highest signal. And importantly, so among the oscillometry parameters we examined, the change in post-bronchodilator R5 was the only significant corticosteroid-related response that we saw with our oscillometry indices. That was the only significant finding. So taken together, these findings suggest that oscillometry provided 2 distinct and complementary types of physiological information across our T2 inflammatory groups. First, at baseline, AX percent predicted increased progressively across our T2 groups. So this suggests that patients with higher T2 inflammatory burden have greater baseline small airway dysfunction. This is clinically meaningful because the inflammatory phenotype, which was defined by blood eosinophil count and FeNO, is associated with measurable differences in our airway mechanics. Second, post-bronchodilator change in R5 was the only oscillometry parameter that demonstrated a significant corticosteroid-related change over the 7-day period. The other resistance and reactance-based indices were examined. They did not show any statistically significant treatment-related response, which is an interesting finding and worth discussing. For reference, here's a side-by-side of the results from the original PRISMA study, where spirometry showed the clear graded improvement in post-bronchodilator FEV1. And here is our corticosteroid response with post-bronchodilator R5 change. So to conclude, the PRISMA framework investigated a personalized medicine approach to acute asthma management, and our analysis extended the framework by adding oscillometry and adding an additional physiological layer. Oscillometry provided insight for both baseline airway dysfunction and physiological changes associated with treatment with the 7-day course of oral corticosteroids. So future studies can determine whether combining these inflammatory biomarkers with oscillometry could improve acute asthma phenotyping and help identify which patients are most likely to demonstrate an objective physiological response to treatment. So ultimately, oscillometry may provide like a useful bridge between biomarker phenotype and airway physiology during asthma attacks. Thank you for everyone who made this project possible, and thank you for listening.
Well, I hope we'll all agree that Rachel's done a bang-up job with the presentation and to be congratulated. The question is, what do you guys think of the data? My comment to start it off with is that we may have timescale differences. We have clearly stepwise response of dysfunction at baseline, which we would expect. So it confirms that oscillometry is measuring sicker patients and grading them like the profile of inflammation. Now at day 7, we have spirometry changes for the better, but really unimpressive oscillometry. So the question would be at week 2, week 3, and week 4, what do you think the answer might be, Rachel?
You mentioned that with another study on week, like it was 28 days instead of 7 days, and the oscillometry data actually was very constant. So there wasn't a significant change in most indices, which is surprising. And you mentioned that spirometry also didn't capture.
This is
Spirometry captured the change, but oscillometry didn't.
I don't know if Nirmin Diab is out there. She's joined us recently from McMaster in the asthma space, and she's generated some very nice data looking at that. And it would seem, Nirmin, if you're not out there, I'll speak for you. It's looking like indeed the small airways dysfunction is slower to recover. So when we're deeming our patients recovered spirometrically, we're actually underestimating disease burden, is I think what's going on. But I'd love to hear from other people who have experience deploying the oscillometry in the asthma space. Charlie.
Well, this is really old data from the world of dynamic compliance. That a viral infection will cause dynamic frequency dependent lines to be abnormal for like 6 months. Yeah. And so that was well known. I think it's part of the reason why in many clinical studies you don't recruit patients who are post-viral, and they recommend to go out to 6 weeks, which of course not violent.
But we really don't know at what point, because there were also those papers we pulled up at the time of COVID, I remember, that looked at acute influenza in otherwise healthy young adults. And it also showed the same discord between the spirometry and the frequency dependence of resistance as measured by, I think, serial monofrequency measurements back in the day. It was quite an old study.
So when you say that...
Well, Ron,
Charlie, do you want to finish your comment? And then Jason will chime in.
So
yeah, go ahead.
You've been treated with steroids. You say spirometry. What do you mean by that? Is it the FEC or the FE?
Well, I don't treat kids, but in the adult world, I pay attention to both the FEV1 and the FVC because its improvement will, in my mind, mean there's less gas trapping, which is, the most subtle of the things that we're going to see in the conventional PFT lab.
But this data is from kids, is that?
No, adult.
Oh, it's from adults.
It's adult. Yeah. Okay, Jason, we're all yours.
Yeah, allow me to make a suggestion about what I think may be happening here. If you have Th2 inflammation, you're going to have thickening of the mucosa and extra mucus secretion in the lung periphery, which is going to predispose to mucus plugging, fluid plugging, airway closure. And that will cause AX was your main parameter, wasn't it? It's going to cause AX to increase. So, and when you eliminate that inflammation, all the gunk down there in the peripheral airways will disappear. It will go back to normal and AX will improve. But when you do spirometry, so basically the main event that's going on physiologically is not airway bronchoconstriction. It's airway closure due to crud in the lung periphery. This is my thought. And certainly this is what happens in mice. So when you do spirometry, you take a very big breath, and that may transiently pop open a lot of those airways, which are normally closed if you're just quietly breathing at FRC. So that's going to then have an effect on FEV1 because you've opened up things that were previously closed. So I would expect the maneuver that you go through in order to perform spirometry is going to affect your measurements in a way that doesn't happen with oscillometry because people are quietly around FRC the whole time.
It doesn't happen in traditional oscillometry as we deploy it, but we can also think outside of the box. And one way around that would be to do a quasi-static deflation from TLC while measuring oscillometry and look at the mechanics over the full range of the volume. People have done that trying to estimate airway compliance, but I don't think it ever caught on. I know the Australians were doing it. Maybe people in the room have experience or
Just a comment about that. It's a good idea, Ron. One thing you've got to remember though is that airway closure is not just a function of lung volume. It's not like it's a function of time as well. If you take a big breath and then you go back down to FRC, you don't immediately return to the closure profile as you had before. It takes a while for it to manifest because you're going to have fluid flows and liquid plug formation and this kind of thing. So just bear that in mind when you're thinking about that type of
and it's going to be very heterogeneous between patients too, because different patients are
oh, for sure. Yeah.
Different contributions of these things. Anybody else want to make a comment? Eric?
I just had a comment, two things. Can you say then if you have a patient with asthma who you're not sure how severe they are based on the history and you find residual small airway findings that they have worse asthma, that's just a given. Is that true?
I think it is true because in my clinical practice, everybody gets a traditional workup with a complete PFT plus or minus methacholine on entry. But once they've got established asthma, I actually follow them uniquely with oscillometry. And I found it very helpful to actually pick up non-compliance because I'll confront people who've previously had good oscillometry findings, which are now significantly different. And I'll just say to them point blank, you're not taking your medications, are you? And then I get the confession. And then the next time they come back, their oscillometry is back to normal. And they'll even misreport their ACQs that they're doing and appear to be healthy on the patient-reported outcome. So
is it sicker clinically than you?
No, not even.
Not even.
Relatively well people will have abnormal oscillometry, which can be reversed with therapy. And I don't have enough numbers, but I know in my own practice, looking at the data, there is between a doubling and a tripling of exacerbation rate likelihood in the next year if your oscillometry is abnormal. Well, that's how it's coming together in the real. I can't run statistics to show you, but that's the clinical impression I'm having. And it's people like Rory Chan, who's working with much bigger numbers, that are actually going to convince the scientific community this is so.
And I had another question about this volume effect or the effect of lung volume on spirometry versus oscillometry. And when you're studying this in a practical sense, you don't have shots at someone coming in on different days. And what is the time course of the we do oscillometry first, but then you do some other measurements. You might repeat oscillometry later. What is the time course of this? How much volume?
Okay at 15 minutes.
Pardon?
Yeah. The thing is that
15 minutes.
Some people will bronchodilate and others will bronchoconstrict. So they go both ways. So I've never done it, and I've never read a paper that looks at, every 15 minutes for the next hour. I think Raffaele, it was Jeff, you guys had constant impedances over 15 or 20 minutes back in the day, and you might be able to shed some light on this question that Eric has raised.
That was, we didn't actually look at what they were doing with their lung volume. If they took big breaths during that 15 minutes while the oscillometry, can't really say what's happening. But Ken Luchin did experiments where they put big breaths in, and did oscillometry to watch the recovery of resistance. It goes really far down when you take a big breath, and then does it come back with a bronchodilator or without a bronchodilator? And people with asthma without the bronchodilator, it comes right back. So it looks as though it was bad before and it was bad after very quickly. Actually, this was methacholine as well. So with the methacholine, people who took a big breath who didn't have asthma, they had a beneficial effect that maintained for quite some time. The oscillometry took a long time for it to re-narrow. If the fact that they didn't have the choline brings their airway back to narrowing.
Okay.
If the same is true in bronchodilator, then you don't see much. It's spirometry. You might see if it's dependent on the recoil and you open the airways, you'll see it because spirometry, as to Jason's point, does the maneuver that allows you to see the effect of the bronchodilator. So you have it. But if their asthma and their tone is still there, or that the mucus plugs come back soon after the spirometry or any big breath, then the oscillometry will show no change.
Good. We're going to leave it at that because we're not going to run. I'm going to hand the podium over on time. So Rachel, thank you very, very much again. Okay, so now we're going to bring on Milan Sobani, who is, although he's from Derby in the UK, he's cycling in Romania right now, and he's gotten off his bicycle to give us this talk. So if you're out there, share your screen and welcome to the seminar.
Good afternoon from sunny Romania.
Wow.
Can you hear me, guys?
Yep. And go on to presentation mode now. We're in your slide deck.
Lovely.
Excellent. Take it away.
Fantastic. Thank you again, Ron, for inviting me, to this great meeting. I can see that all of you are living and breathing oscillometry, whereas this is something relatively or very new for me. I'm usually doing more ventilation and so on. So the topic of my talk today is role of oscillometry in COPD, current evidence and directions. I'm Milan Sovni, one of the respiratory physicians currently based in Nottingham, UK, with visiting professor at University of Derby. I'm lead clinician for acute and complex ventilation. And mainly I'll be talking about role of oscillometry in pre-COPD. This is the Indian Early COPD Assessment Network study, or ICAN study. I'll be presenting the results, and the manuscript is ready, so we'll be submitting it very shortly in the next day or two. Right, okay. So my conflict of interest are as declared on the screen. I'll straight away dive into the talk. So COPD, so it's one of the leading causes of morbidity and mortality worldwide, but it's often diagnosed late, and it's been now known for a long time regarding late diagnosis. So Peter Calverley and group in 2011 thought, what about oscillometry? Could we look at that? And looked at patients with COPD, so gold stage 0, but also gold stage 2, 3, 4 as well. And what they found is that even though they had significant abnormal spirometry, a bunch of them had relatively normal oscillometry. And they said that, well, maybe, it has got limited value in diagnosis of COPD. More recently, there has been a significant increase in something which is now labeled as pre-COPD, and a while ago it used to be labeled as gold 0. This is seen in 7 to 8% of individuals in population studies, either smokers or biomass fuel exposure. And these are smokers or biomass fuel, but although they are symptomatic, their spirometry is absolutely normal. So they will have symptoms there, and this kind of proves a diagnostic and therapeutic uncertainty. And we see a fair few patients where you think that they have got COPD, they walk like ducks, quack like duck, but you do spirometry and it's not a duck. So what do you do? So that kind of started this project really a few years ago. These guys also have got radiological changes, as it happens these patients with pre-COPD, so thickening of airways, emphysema, and they have also got lung function issues, reduced gas transfer, and they drop their FEV1 by more than 40 mL per year. So similar to COPD patients. They do have reduced alveoli number, they get exacerbations, they need treatments, and they have significant small airway dysfunction, which is a key. And as you guys all know, you are the experts in this field really, 8 to 15 generation small airways, so vast total surface area, and spirometry is not the best tool. And more recently, number of studies have shown that oscillometry indices correlate better with imaging markers of small airways disease. So what we thought is that, okay, so spirometry is not doing the trick for pre-COPD. Can we look into oscillometry? And we were specifically interested. We are specifically interested in looking at AX because the area under reactance correlates with lung stiffness and loss of elastic recoil, which is where we think, and the studies show the COPD or pre-COPD may start, and that's what we were interested in. When we looked at area under the reactance curve, so AX, of course, so what we thought is, okay, so how do we go about it? So you guys are all sort of proper scientists and, looking at the mechanistic view, whereas I'm a clinician, although I do a lot of research, it's mostly clinical research. So I'm looking at it, how can I look at oscillometry that can be used in clinical practice by somebody like me? So we looked at the literature, we looked at various values of AX that are seen in healthy volunteers, those in asymptomatic smokers, symptomatic smokers with normal spirometry. And then we also looked at a paper by Brian Lipworth where they are proposing a cutoff of AX of more than 10 for diagnosis of COPD. We then thought, okay, we will settle with AX cutoff of more than 6 to balance sensitivity and clinical usability for pre-COPD. This cutoff should be a pragmatic one. It should be useful by Joe public, in your GP practice or not just in a tertiary center who are doing oscillometry and know all about Z values and Z scores and so on. And we thought, could we look at a similar marker that we use FU and FVC ratio less than 0.7 in COPD? Could we look at something like this in pre-COPD? Right, so with a lot of preamble, so that's what we said to do. So the questions were, can oscillometry help diagnose pre-COPD? And can it help identify a phenotype, that dreaded word, that can predict response to treatment? So what did we do? A double-blind placebo-controlled randomized controlled trial where we compared treatment with fluticasone and vilanterol once daily versus placebo over 3-month period. And why did we choose LABA-ICS? Because as we know, the Rethink study, which was a LABA-LAMA study, in pre-COPD cohort, it was proven negative. Plus, we were going to look at an Indian cohort where biomass exposure was also going to be an issue, and that is associated with Th2 inflammation, where in that cohort and in others, ICS have also been shown to decline, slow decline in lung function. So we therefore set off with this study. Inclusion criteria were informed consent, of course, young individuals aged 35 to 55 who are not obese, smoking history more than 10 pack years or equivalent exposure to biomass fuel, post bronchodilator FEV1 FVC ratio more than 0.7, COPD assessment test or CAT score more than 10, and importantly, we ensure that they have to have AX of more than 6. So this is 6 centimeters per liter per second. So AX more than 6 using Tremoflow C100. So what this demonstrates is that we used oscillometry to actually include and exclude patients. So exclusion criteria were previous diagnosis of asthma or COPD, previous history of use of inhalers or oral steroids, inhaled steroids or oral, or history suggestive of asthma, so symptom onset of less than 30 years. Now, because we thought that it's not going to be an easy study to recruit, so we looked at 10 centers across India, and these are the centers, and this is the team, and I'm really grateful for all the hard work the PIs and their teams put in. Right, so power calculation. So it's important to remember this was an exploratory study, and we didn't have any data at that time, at least, of studies using oscillometry as a cutoff. So we anticipated mean CAT score of 15, dropout rate of 20%, and we thought we'll need to recruit 196 subjects to give us a good power to detect change in CAT score of 2. Why 2? Because 2 is MCID for CAT in COPD, and we thought if it's 2 in COPD, we could use that for pre-COPD as well. What were we interested in measuring? The primary endpoint was change in CAT score from baseline to 12 weeks and change in AX. And then we wanted to look at number of other spirometry parameters, exacerbations, rescue medication use, and so on. Importantly, there were some exploratory aspects to it. We also looked at the HRCT at the baseline. We looked at metabolomics at baseline. And we thought, well, we'll see whether it helps us give a cutoff with eggs for pre-COPD. If I'm going too fast, please let me know and I can slow down. If it's okay, then I can carry on.
No, perfect. Actually pick up a little bit of pace because
Okay.
I want to make time for your discussion.
Right, thank you. So this is the consort diagram. We assessed 149 patients, randomized 93. You will have the video subsequently to go through it in detail. The key figure to remember is that we lost a good number to follow up. So we finally, 28 in each group completed the study. This included a bunch of patients saying it's too cold in the winter in North Indian centers. We are not going to come back for study visits. Baseline characteristics, groups were well matched, mean age 45, so relatively young patients for COPD, about 80% men, about 80% smoker, 20% were biomass fuel exposure, and most people who were doing biomass fuel exposure were women. So smoking wise, about 14 to 15 pack year smoking history and about 19 to 20 equivalent of biomass fuel exposure. Again, CAT score was 15.8 in FFV, and we had 14.8 in the placebo group. So very well matched groups, really. We looked at eosinophil count as well, and the mean count was 266, which is very similar to the Indian COPD population. This is based on data from a few thousand patients with COPD in India. Right. So spirometry, again, the groups were very well matched, and importantly, they had pretty normal, high normal spirometry really. So mean FEV1 and FVC were more than 90%. Ratio was about 80%. So no difference, but importantly, high normal spirometry. Looking at the FEF 2575 data, using that, we would have missed small airways disease in about 55% of individuals, just highlighting again, oscillometry performs better. When we look at the R5 minus 20 or R5 minus 19, whatever flavor you want to say. So, and eggs data, we can see that these are not normally distributed, which again wouldn't be something different to you guys. Important thing is that the groups again were well matched, and median eggs was 12.4 in group A and 13.8 in group B. So again, pretty well matched groups really. Coming to the results. So we have looked at the first patient recruited in Feb 24, last patient in March 25. So baseline to second visit, 67 patients and 56 patients completed all 3 visits. So we used carry forward data from second visit for 11 patients and used data from 67 for results and analysis. So main results, what did we find when we came to CAT score? Both groups improved, but there was significantly more improvement with FFV. So fluticasone vilanterol compared to placebo. And this was not only statistically significant, but it was difference was 2.47, which is clinically significant. When we come to oscillometry data, there was no change, no difference, within group really in R5 minus 19, whereas for AX, there was improvement within group as well as significant improvement in both within and between group. So this is a table with all the parameters. I'll give you 30 seconds to have a look at it. Just basically very minimal or no change in any of these spirometry parameters. Good CAT score change and significant change in X, but not in R5 minus 19. we had actually captured compliance objectively, and patients had high compliance and relatively low use of rescue medication. The reason we wanted to do that is to make sure that any results we are seeing are related to medication use. There was very little or no correlation between baseline eosinophil count and CAT score or AX and change in AX. Right, so comes conclusion time. So we know that that this not asthma, there is no correlation between eosinophil count and baseline, plus no previous history or treatment. And FFV, with FFV, it improved AX but not change in R5-19. But more importantly, when we looked at their HRCT, there was emphysema in 23% participants, bronchial wall thickening in 16% participants, and 25% participants had emphysema as reported by the FDA-approved lung density analysis software. So this is a pre-COPD cohort. And interesting finding from our point of view is change in X but not R5-19. So this has been reported in some other studies as well. SARS is not the only study. And as we said, X is not normally distributed. If we had used Z scores, we would have missed 27% of subjects, because in 27% of subjects at baseline, their X was less than Z score of plus 1.64. About minus 15% change in AX with fluticasone. So, more sensitive to detect small airway change, not only at baseline, but response to treatment. And because small airways can then over time proceed to overt airflow limitation, so this can provide a therapeutic target. And this is just a, just a little, just a little sort of profile from Brian Lipper's group from last year, demonstrating how various markers respond to bronchodilator change, and AX seems to be doing pretty well in their study as well. So I think it's really important we need to look at our patients carefully, whether they have got large airway disease, whether they have got small airway disease, what is the pathology and how do we treat. And coming towards conclusion really, so in symptomatic individuals, we would like to think that with normal spirometry, there is a group that have got AX more than 6. And what this shows is oscillometry is more sensitive than spirometry for small airways dysfunction. AX can potentially, AX cutoff of more than 6 can be used to diagnose pre-COPD, but does need validation in larger studies, and it proves as a treatable trait as well. Important thing is when we looked at our data, those in the lowest quarter of AX, so AX for example 6 to 8, they also had improvement in symptoms and oscillometry. Had we used a higher cutoff, we would have missed these guys. So AX of 6 worked. Whether it can be used any lower, I don't know. Further studies will hopefully shed more light. So this is the first study where we have used AX as a cutoff, first positive study for pre-COPD, and one of the first studies where they have looked at both biomass and smoking in a pre-COPD context. FFV was not a not extra fine particle, just fine particle. So it would be interesting to see what happens if somebody uses extra fine particle. And again, we found use of HRCT really helpful. So we will need further validation for AX and a treatment effect in larger studies in low middle income countries as well as Western populations. I think really need to use extra measures, for example, incentives and help to attend the follow-ups and so on, so that patients don't drop out easily. We are still working on the metabolomics X5 and expiratory flow limitation analysis. This is the study team. Thank you again for listening, and happy to take any questions.
I'm going to take the MC prerogative and say we'll be discussing your work over coffee because we've actually run out of time, but your message is well received, and Sandeep is sitting just over to the left of me. So he's going to speak to us on our behalf, and I might actually let him just say one comment, but we could go on for hours about absolute versus percent versus Z scores, and Sandeep and I share some views here. Congratulations, because Milan, you are a clinician just like I am. So don't apologize. You have to do the data like that to see it, because if you just did the individual patients like we see in our clinic, you would miss the signal. So thank you for sharing this study with us. Sandeep, do you have any quick comment to make?
No.
So there you go. We say a perfect study. Hope to meet you at ERS if you're going, and,
Yes,
and hope
yes.
to see you in person next year at the seminar. Have a great rest of your vacation.
Absolutely. And hopefully we can contribute and work together and collaborate for future studies.
Okay, great. Well, have a
Thank
good
you
day.
again.
Bye.
Cheers. Bye-bye.
Okay, well, Vincent from Washington, not from Boston. He's from Seattle, I believe, is coming up, and I'm very sorry about the confusion, but I know Vincent because of these rounds that Chung Wai organizes once a month between Toronto, Montreal, Boston, and Washington. And I've associated you too strongly with Eric. So welcome to the podium, and I'll let you introduce yourself properly. Oh, are we sharing the screen, guys, online? Oh, no. Let me just fix this. Oopsies. How come I'm gapping here? Well, you're here. Okay, share. Okay, that's what I did wrong. We should be able to go now. Are we seeing it online?
Yeah.
Okay. Take it away.
All right, thank you. Yeah, thank you, Ron. Thank you for the introduction, and thanks to the group for letting me present some of our data. This is actually an update on a presentation that my colleague Eric Garshik made at last year's conference. I am new to this conference, and I'm new to oscillometry, so I really am interested in everyone's feedback. Again, this is a presentation on the large and small airways dysfunction in veterans with environmental exposures. I am at the University of Washington in Seattle. Just in terms of disclosures, I have grant support both from the Department of Veterans Affairs and a NASA grant looking at wildfire smoke. So in terms of the reason for this study, as many of you know, several million US soldiers were deployed to Iraq and Afghanistan in the post 9/11 period, and these soldiers were exposed to a number of occupational and environmental exposures that we have on the slide. The first is ground dust. Soldiers were exposed to ground dust during convoys and during various military operations, and then there were these dust storm events that would occur. The second exposure is burn pits, and there was a lot of interest in this in the United States. Soldiers didn't have a good way to get rid of waste, and so they would burn their waste in these large open pits. They would burn everything from human waste to computers to uniforms, and were using jet fuel and other fuels as accelerants. So many soldiers were exposed to the fumes from these burn pits. Engine exhaust, such as from tanks and trucks, and other open combustions from burning vehicles and other combat-related combustion. And then finally, just being in the military, there are a number of job-related exposures that these soldiers had to vapors, dusts, gases, and fumes. Things like vehicle and aircraft maintenance. So what are the respiratory effects of these environmental exposures that these soldiers experienced during their deployment to the Middle East? When we look at, there's 500,000 veterans who are in the burn pit registry, and looking at those survey responses, a large number report respiratory symptoms. Epidemiologic data has shown that 24 to 30% of veterans who return from deployment are then diagnosed newly with asthma. And what I think is really relevant in terms of small airways disease is that there were several case series where they've done lung biopsies of veterans with unexplained dyspnea and have found findings of constrictive bronchiolitis. The group at National Jewish has proposed a couple different deployment-related airway diseases, including distal airway disease, which they've called deployment-related distal lung disease, which would include constrictive bronchiolitis. And then there's a more proximal airway disease or deployment-related asthma. Up until this point, most of the PFT data in these large cohorts of veterans has been actually focusing on patients who have respiratory symptoms and have not included those who are not symptomatic. To try to address this, the VA has done a couple of large studies. We are participating in a study called the SHADE study. This is funded by the VA. It's a epidemiologic study to look at the effect of environmental exposures on lung function. The SHADE study has now recruited more than 4,500 participants at 6 sites. They enrolled patients who had land-based deployments, so primarily Iraq and Afghanistan. These participants are not selected based on symptoms, but they're randomly selected based on Department of Defense rosters, and they lived within 25 miles of the participating VA medical center. For the study that I'll be describing today, called the LEAD study, we invited participants from the parent study to come back to do some more physiologic testing. So we recruited from 4 of the participating sites, Boston, Houston, Minneapolis, and Seattle. And these participants were invited to come back and do a second visit in which we assessed respiratory symptoms. We did exclude patients who had a significant smoking history. We did exclude patients who had COVID that was severe, that required either hospitalization or oxygen therapy. During both the parent SHADE study and the LEAD study that we did, we assessed symptoms, so dyspnea, which we described as shortness of breath on level ground or walking up a slight hill, chronic cough for more than 3 consecutive months of the year, and self-reported wheeze. We also captured whether or not they had a physician or healthcare provider diagnosis of asthma. And all participants did spirometry, so both the parent SHADE study, so the 4,500 patients, and also when they came back and did this LEAD visit, they did spirometry, but we also did forced oscillometry with the Resmon Pro. This is a description of the cohort. This is a small group of patients, 126 patients that came back. The majority were male, 85%. The mean age was 46.8. The average BMI was 31. We had a very low number of former smokers at 13%, with only a 1 pack year smoking history. They were 14.8 years after they had served in the military, or sorry, I should say after they were deployed in the military. And this was 4 years after their initial SHADE visit. We divided participants based on their symptoms. So we looked at their initial symptoms when they came in for their first visit, and then their symptoms at the second visit. And there were 70 participants who never reported any respiratory symptoms. 22 patients, who had symptoms at the first visit, but not at the second. 20 that had symptoms at both visits, and 14 who developed symptoms between their first and second visits. As you can see from this slide, most of the veterans reported actually wheeze and cough and not shortness of breath. 85% of persistent symptoms had cough, 75% had wheeze. A number of participants did have a physician reported diagnosis of asthma. So 50% of persistent symptoms carried that diagnosis. As you can see, most of the diagnoses were made after their deployment. And a number of participants were using an inhaler for their lung disease. So when we looked at differences in their pre-bronchodilator pulmonary function testing, we found that there was really no difference in pre-bronchodilator oscillometry. And when we looked at spirometry, there was just a small difference in FEV1 to FVC ratio. So you can see on this slide, we again have the different categories: never symptoms, symptoms that remitted, persistent and new onset symptoms, which were 34 participants. And there was just a slightly lower predicted FEV1 to FVC ratio at 94% predicted, which was just a little bit worse than 97.5% of the never symptoms. We then looked at the post-bronchodilator response, and this was just looking at pre to post within each group. and using just a paired t-test. And we found that among the never symptoms that there were very little changes with bronchodilator, with just a change in the resonant frequency. Those who had symptoms that remitted similarly had no real change in oscillometry with bronchodilator. But those who had persistent or new onset symptoms had significant improvements or statistically significant improvements in R5, R19, X5, AX, and the resonant frequency. All the groups had a small improvement in the FEV1. We then compare the different symptom groups and looked at the bronchodilator response between the different groups. And again, the first column is the never symptoms. The second is those who remitted, and then comparing remitted to never, there was really no difference between those groups in terms of their bronchodilator response. But when we compared the persistent or new onset symptoms to the never group, there was a difference in that group. So there was a significant difference in the R5, R19, and the resonant frequency. And there was also a difference in the bronchodilator response in terms of percent change in FEV1 and FVC. So suggesting really there's both large and small airways changes in bronchodilator in this group with symptoms. So in summary, in this group of participants that were not selected based on their symptoms, we found that cough and wheeze were the most common symptoms that were reported and not dyspnea, which had been seen in other cohorts. There's really no difference in baseline pre-bronchodilator oscillometry, but that with bronchodilator, we saw a statistically significant improvement in both large and small airways measures for both oscillometry and spirometry. Admittedly, these are below the typical threshold for a significant bronchodilator response, but we do wonder whether we may be detecting early airways abnormalities in this group, and that perhaps we are identifying subclinical deployment-related asthma or other deployment-related distal lung disease. So I'll stop there. Thank you.
Thank you very much for sharing that data with us. Are there comments from the audience or online? One of the things I noticed in your data was the forced vital capacity sort of had a borderline improvement, suggesting that we're dealing with very subtle lung disease and there may be becoming less gas trapped for treatment. And I guess I would also take away from your data that we really need both methodologies if we want to capture everybody. But these are very subtle findings. I'm just trying to think of other veterans cohorts that have been looked at that have shown more dramatic changes. It seems to me some of the stuff that was coming down. There's a guy, Sammy from Long Island, I think was also looking at some stuff, and I thought he had more impressive findings in his post-deployment. Are you familiar with his work?
I'm not, but I think part of this is that we're looking at a group that wasn't selected based on symptoms, and like the group of National Jewish, and the VA does have a group that's looking at patients who have significant unexplained dyspnea, and they are seeing differences in PFT results and differences in spirometry, in oscillometry as well. So I think we're looking at a very mild, changes.
Well, I think it's very important to continue through it because these guys have, put their life on the line for their country, and then to pass them off as, malingering because we can't identify their symptoms with traditional PFTs really underscores the role that we need to throw everything, including oscillometry, at these guys, so that they A, can get a diagnosis and a treatment, B, whatever compensation they need, and just reassurance that we're behind them and think that they're after serving, trying to take advantage of the system.
I couldn't agree more, and I think part of what we're dealing with this issue of constrictive bronchiolitis is it's very difficult clinically to diagnose. We do CT scans with inspiratory and expiratory images, but for many of these participants or patients, we don't see a signal in terms of spirometry. So I think oscillometry is going to be a really nice addition to the evaluation.
Well, you'll be happy to know that Jonathan Odette from the Quebec Veteran Foundation is over there in the back. And I think he's quite eager to connect with both you and Eric to share some things. So I just wanted to shout out Jonathan so he could network appropriately. Hey,
Ron.
We still have 5 more minutes so we can keep the conversation going here.
Can you guys hear me? I'm online. This is Danielle Glick.
Hey, Danielle, so sorry that you couldn't make it. Can you turn your camera on so we
Yes, I can. Hold on one second. Hi, I'm joining you guys from home. I was supposed to be there and my flight got canceled. I think perhaps the wildfires and the heat had something to do with that. So anyway, thank you for still having me. And I actually am part of the post-deployment cardiopulmonary evaluation network, the PDCN. I work closely with the group out in Denver, and we are based from the risk in New Jersey. There's 6 sites throughout the country, and so I think we're the group that you were referring to with the unexplained dyspnea. Now we are a symptom-based or symptom-driven cohort, so we are looking for veterans who have symptoms and that are unexplained. We're still in the process of kind of trying to go through all of our data because we are still actively recruiting all of these veterans and hopefully adding a longitudinal component to it as well. As yet, our spirometry is similarly not impressive, but our oscillometry, we've noticed abnormalities, but not really in any particular phenotypes or cohorts. So that's something that we're digging into. So we are seeing some signals, but again, working hard to kind of classify what that looks like. I've been furiously taking notes, kind of interested in the ways in which you guys are really looking at this and trying to determine abnormality. I think, one thing that really stood out to me already was perhaps looking at, PRISM. Is that maybe a clue to where we could be looking at this and the differences in FVC as well, if that's an area that we might pick up abnormalities, but we're also kind of seeing abnormalities, but not in a particular way. So, I'd love to connect. Fortunately, it can't be there, but please reach out. I'd love to learn more about what you guys are doing. And Eric, I know you guys are very familiar with our group as well, so happy to connect on that too.
Good. Well, we'll see you at the next meeting if you're over ERS, and even better, hopefully we'll see you in Montreal next year at the seminar.
I would
The
love that.
airlines and the environments or the wildfire.
Yes.
I saw some other hands going up in the room. So Charlie.
So you made an interesting comment that the bronchodilator response is kind of below the threshold that most people would consider significant. And so as you're a clinician, correct? Are you still going to treat the patients? It's a loaded question.
It is. I mean, this cohort again is an epidemiologic cohort, so we don't have an immense amount of clinical data.
Well, are you a betting man? Would you bet that they're going to be treated with drug?
Well, that I think our experience has been that many of these patients who are symptomatic do get empiric treatment, kind of regardless almost of spirometry or instead of spirometry, or even an oscillometry is obviously less available. But I would prefer that patients have a diagnosis.
Well, the reason I'm smiling is one of my mentors in the benefit group, Charlie, one Canadian, and he used to say that this was your mother, we treat them with bronchodilator. That's a rhetorical question.
Well, that's also something that I use clinically teaching.
Yeah.
You want to never make a mistake. Right. You ask yourself, what would you do if it was A, my mother, B, my father, C, my sister, and D, my brother? And you go forward and be relatively safe as you treat patients through the years.
That's right.
Leonard.
Yeah, I guess connecting a bit here because you never mentioned anything about the eosinophils or pheno. I suppose we probably have looked into that. Then what kind of profile do these patients have? Are they TH2 or TH1, or because that could also implicate what kind of treatment you select?
We do have that data. Unfortunately, we haven't finished our cohort. We actually now have about 300 patients in this group. And so we're going to analyze that. We're finishing our recruitment in August, so we will have that data, but we don't have it right now.
Yeah,
but we will have eosinophils, and we will have also CT scans to look at.
I mean, do you think these people got sensitized to anything, or is this more a sort of chemical reactivity?
Yeah, it's interesting to think of what type, when you think of asthma, whether this is more of an occupational related asthma versus a kind of what we think of a typical kind of sensitization. I don't know the answer to that.
Will be interesting.
Yeah.
Well, we'll continue the conversation to coffee. It's 10:15. Please note that I'm handing over the podium exactly on time, and I'm hoping all the other moderators will do the same. So thank you very much.
Thank you very much.
Okay, talking outside, everybody. Those who are talking next, please see Chung Wai to give your your talks on USB. And all moderators, make sure that you connect with your speakers over the next hours to likewise get them all organized up here on the screen ahead of your moderating sessions. Thank you. See you guys in 20 minutes. Back here, please.
So if I could have everybody's attention. Hello, hello. Larry, Larry. Okay, we're going to start our next session. Gives me great pleasure to introduce Eric Garshik from Harvard at the VA hospital. And he tells me he's going to extend on the previous discussion and talk that we had and take it away.
Great. So I'll bring this up. I think you right here. Okay, great. Well, good to be here. I just want to thank Arnold for inviting us and helping us with understand oscillometry that we've been applying to our research. I work closely with Vincent, and this is talking about a follow-up study that's recently been funded by the Department of Veteran Affairs. And I have similar grant support with Vincent. We work closely together, and some royalties from UpToDate. So just talking about our cross-sectional study, for which the sample that Vincent spoke about was drawn from. This is our SHADE study, which was designed to assess the effect of PM 2.5 particles 2.5 microns or less during deployment with association with pulmonary function assessed by spirometry and symptoms. And so we're using a military job environmental exposure questionnaire, and the deployment periods of interest are in Afghanistan 2001 to 2021 and Iraq from 2003 to 2011. So this is so in our baseline study, all we have is spirometry, pre and post spirometry data and symptoms. We recruited previously deployed veterans in 25 miles of 6 VA centers. And the unique thing about this study design is we get a very detailed deployment history using a Google Earth map with all the bases on there. And they go through and tell us what time period they spent at which base, since that's not available from DoD records. We do health questionnaires and spirometry. The target sample size is 5,200. We've got 4,700 now. We had to do about a 3-year break due to COVID and had to restart up the study again. The response rate is near 30%. And these are drawn from the deployment roster, and the characteristics of the people we're getting in are virtually identical to the people who aren't coming in. So we feel it's fairly representative. And just how we're getting the exposure information on PM 2.5 is using NASA satellites based on this AOD metric, which is based on light scattering. And through some complicated modeling, you can actually get estimates for PM 2.5 in a 1 by 1 kilometer grid around the deployment countries of interest. And that's being linked to PM 2.5. So what about the question of longitudinal change over time? And this is a conceptual model. Yeah, here it's so our cross-sectional, the logical question to ask of our cross-sectional study, regardless of the results, if we don't have the results yet, is what's happening longitudinally. So if you have end of deployment right over here, and this is our baseline visit 1, the SHADE study, we're seeing people on average 12 and a half years post-deployment. And let's say we find a decrement in FEV1, we can't tell whether it's going down continually or whether they took a hit with deployment and it's now not going to go down. We also don't know about small airway disease and a bunch of other things. So our study design, you extend the follow-up with 2 visits, visit 2 and visit 3, that we've proposed, and that theoretically could give us information on FEV1 decline and other characteristics that occur at this point. And at this point, and given the 3-year hiatus with COVID, it even gives us a longer time post-deployment. So this would be on average 25 years post-deployment and 30 years post-deployment, or on average 12 and a half years after the first visit. So we should see changes in FEV1 if it were present. So that's our conceptual model of lung function loss. So, and this, we wrote up the proposal, it just recently got approved. Visit 2 got approved, and visit 3 is contingent on success with visit 2. And we are going to, our current study is going to run through 2037, coming up in about a year. And we're starting up the second visit in January 2028, trying to get people on average at least 5 years after that visit. We're probably going to have more than 5,200 people. We're paying them $250 now to come in. This may be a generous response rate. We are powered to see effects at lower response rates. So let's at least have several thousand people coming in, hopefully here. We're going to pay them $500. And once you're in the cohort, we expect a higher response rate. This is projected through 2037. Of note, we have a succession plan for the principal investigators of the study, given the long time period. So that was actually a good comment by the review committee. So at the study visit, we're going to update respiratory symptoms and asthma. And we piloted that people with persistent symptoms or new onset symptoms appear to be different, getting an asthma history. And we evaluate other pulmonary diagnoses plus lung cancer. We'll be doing phlebotomy at this visit, measuring CRP, IgE, some COPD-related biomarkers, getting at eosinophils, and we're going to be doing methylation and DNA. In our pilot study, we have CT scan data. We'll be doing that to get an emphysema, gas trapping, functional small airway disease, and large airway wall thickness, PI10. And then the order of testing is actually the way in our pilot study is pre-bronchodilator spirometry. Then we do, we're going to be doing full lung volumes using the NDD Pro Lab. This is, of course, the Resmon. And we actually the people hold their own cheeks for our study to avoid the issue of technicians touching people. So the order is a slow VC, which you need for diffusion, nitrogen washout, and then you do the pre-bronchodilator spirometry. We're giving 2 puffs of albuterol. You wait between 50 and 30 minutes, and then you do oscillometry, and then the spirometry post-bronchodilator. And this is the same protocol that we've been doing in our pilot study that Vincent presented, the spirometry and diffusion data, the oscillometry data. So the objectives, though, are longitudinal and cross-sectional, since we don't have oscillometry data at visit number 1. We will have it at visit number 2 and potentially at visit number 3 if it occurs. So we're going to be doing the association of deployment PM2.5. In other words, the cumulative exposure, like in microgram years and microgram months, to PM2.5 during deployment, and with our questionnaire that we quantify activity-related exposure, such as working at a burn pit or exposure to dust storm. We have 5 distinct exposure categories that we validated to be different, and looking with longitudinal changes in spirometry, and then association between exposure and persistent new onset respiratory symptoms. And then for the oscillometry, we're going to be looking at association between PM2.5 with the oscillometry outcomes. So that exposure years ago caused changes, 20, 25 years later in oscillometry. And the same thing for our questionnaire. And also, we're going to be looking at CT scan imaging, and we powered this to look at measure gas exchange, diffusion capacity. So I think this will give us associations between distant exposure outcomes years later, but also I think this would be a rich database of oscillometry to look at other things. And the database, whenever you have a database of 3,000 people with oscillometry, and their characteristics, you can do a lot with those data. So I think this is future conference data to be presented in a number of years. So let me just thank all of our people that make this happen, our coordinating center, our co-chairs, site investigators, our exposure assessors, and Meredith Franklin's actually in Toronto, University of Toronto, imaging experts, and our planning committee. So let me just end with that and take questions. Just one of the things. So one of the things I was kind of focusing on was the order of doing the testing. Like we do an inspiratory CT and then an exploratory CT at FRC, probably 15 minutes before the oscillometry. So I think that we just focusing on what's the right order to do this in. Maybe worrying about inappropriate perhaps, but it could matter. Yeah. Yes.
Yeah. My name is David Kashahara, and I saw in one of your slides that you have a range that you're gonna measure. I work with a range, right now, and we are very interested to know how you're gonna measure that range in the circulation. Number one, and second, just to clarify, the range can be have a dual answer, loss of the type 1 alveolar, because if you have a loss of type 1 alveolar cells, your soluble rate probably gonna blunt or gonna be decreased. Okay. But the other hand, persistent inflammation will raise the circulating soluble rate.
Right. So we're using the Children's Hospital epidemiological lab to measure rate. I'm not sure how they do. I've got to refer back to what said they're going to do, but I'm sure it's going to be a reliable measure. I can let you know, but it's going to be a few years away before you get this. But thank you very much for your comment that we may see competing effects. I think that's the key thing, and maybe relate that to diffusion capacity or
absolutely
measure drop out of alveoli or something. Right. That's a good question.
Ron and then Charlie.
I'm reassured to see that you're going to be a long-term attendee of the seminar.
That's it.
And number two, I'm happy also to see that you're partnering up with Raul Estebar as your expert in the CT scan. He's attended this seminar in the past. Okay. He's responsible for my labs being able to do quantitative imaging that we also do. My question is, are you considering doing supine as well as prone CT scans? Is there any incidence of subtle interstitial lung disease in this population that we've brought out only by that maneuver? Because at that early stage, oscillometry shows any of these folks. Is this an issue? Is something you're planning for?
Well, we hadn't. I mean, I would say we have 200 people with paired CT scans already.
Okay.
And in our pilot study, and we've not seen visual evidence of interstitial disease, and maybe the rare ILA. But okay. But visually, Raul actually has some algorithms to do that using CT imaging, and that's one of our pilot projects to do that.
Okay. Thank you.
Maybe as you're beginning to think of it, we haven't started with this.
No. This is we're planning it right now. Actually, the follow-up.
So I didn't see any talks on device differences, and so I think from the perspective of having multi-site studies, number one, what device will using, and as you're following these folks, 25 or 30 years,
right?
How are we going to? Because I don't know if any of the device manufacturers here. I mean, I don't know that what you have, what the half-life of your devices are, but I would imagine not 30 years.
Well, no, so it'll be visit 2 and visit 3 for the Resmod, right? Yeah.
So so maybe I'll stop there.
Yeah, so I mean, the NDD device is, I mean, so it's not based on like, volume measurement, it's based on, flow essentially, the turbulent flow and is, I mean, I suppose over, we're not going to use, we can be using the Pro Lab and not the same devices that we do the initial FEV1 measurement on, but I'm said that's pretty independent of the technician of the device.
Well, I think Shanghai is basically bringing up the results of the paper that Soli, Larry, and I did back in 2019 that showed important performance differences at higher impedances between commercial devices compared to the gold standard, which is essentially Zoltan's wave tube. And sadly, although we've offered our services to now dozens of companies commercializing devices, they've yet send a lot of lip service. Oh yeah, we'll do it, but we haven't received any. So I have a lot of good designs out there ergonomically, but I have no idea how they perform, and I don't know that. So in order to be sure that your very expensive data by the time it's 30 years old is optimally analyzable, it'd be good to figure out which device you're going to do and reach out to that manufacturer and find out what their long-term plans are. Maybe we'll open the floor to the industry here and see if anybody wants to go out on a limb in public and make a comment. Leonard?
You're looking at me. I think, it's this point well taken here. The fundamental difference between, say, spirometry or body box measurements versus oscillometry venous measurement is that in the one case, you're essentially just looking at variables, pressure, flow, and volume.
Yeah.
Which you can, reasonably well calibrate the device for. When it comes to something where we try to measure at different frequencies and then relating the different variables to one another to expect parameters, there's a lot of assumptions going in there how to do that. Also, how do you calibrate your devices? And that's sort of the secret sauce between all the different manufacturers. I think that's why we're kind of a bit about how we do these things. That's just the nature of the business. I think another issue is, of course, and we can just look back historically to manufacturers of medical devices. They tend to be bought up and sold off, and then they reappear again. Look at Jagger. Now all of a sudden that's Jagger again. It's been a couple of different manufacturers of the same device over the past 20 or 30 years. We don't know if we're going to exist as, Thoracis or Tremoflow 5 to 10 years from now, of course.
Well, this is why I think it's absolutely laudable what you guys have done, shouting you out, and the folks from Northern Italy, Resmon. Both devices allow us to export the raw pressure flow. And I think that's the answer to the long term.
Okay.
Make sure you have devices that allow that, because then you can conserve that original data. And over the years, our modeling may change, our parameters may change, but if you have the pressure flow, you can do anything with it in the future. You want a high sampling rate, pressure flow device. And if you leave it at that, there may be other ones that will come on in the future that allow that. But these are the two I know and I've worked with. And that's why I could say those devices you can't go wrong with. And that's about as close as I'll give you a commercial endorsement. I don't know if Raffaele wants to chime in because he's for folks who don't know it, Raffaele is the inventor of the Resmon Pro, who complements Jeff, who's the inventor of Tremoflow.
I agree with on what you were saying. Unfortunately, we know that the complexities also from starting from flow and pressure data to get a reliable impedance, you need some compensation about how the different transducers are impacting your signal. So I agree with Ron that you need to have the possibility to save the raw data, but when you do this, you also need to measure this raw data against some solid gold standard. because every flow and pressure data that you get collect from whichever device will be also corrected for the characteristics of the specific systems.
Right.
So it's very important that you get the raw data, but it's very important that so that you are sure that either somebody else or yourself are collecting data against some devices that are able to resemble the physical condition of the lung that you want to test. This means not only static object, but also object in which you have breathing, changing flow, and so on. So this is something that Tom started years ago. It's something that was working for a while. I think that there's still another step to do in order
There's an opportunity. Yes, we need compliance with industry, and the issue is not with you, your companies, your guys are all in. It's the other manufacturers. So I will put a general plea out to all those online who may do this now or in the future, please, to move the field forward. There are 1 billion people with obstructive lung disease on the planet, and most of them need to be diagnosed. And there's going to be no single device that will do it. I think there's plenty of market share for everybody, and you will advance your sales more by working together than competing. And I'll leave that as my editorial comment. The only other thing I might do is actually draw in a person who's been my mentor and has the gold standard in my mind, and that is Soli. Looking at his watch saying Ron's talking too long.
Actually, I wanted to make a comment, but Rafael did. So it's not enough if we are to the raw pressure flow signals, because they can be measured at different standards. So that's all.
Yeah, so I think what you're saying is that you have to make sure machines are not changing over time that you're using, and so you need to have take your machine and have a test signal into it that would actually give you back some characteristics that are not changing. Is that what you're saying?
Let me talk to you offline,
Okay,
so
right,
I answer the question properly, because it's a little bit more nuanced than that.
Right.
And we're 1 minute over time, and
Okay.
Jason is waiting.
Right.
I'm gonna ask.
It's very helpful.
Can I just say one thing? So for ventilators, we have test lungs, right? Where you can purchase a system, the known compliance and known resistance, and it will take active breaths, right? Very precise. You can test your ventilator. Is there a similar device for oscillometers? Where you
my garage.
Old standard.
In my garage.
Very good. Well, Ron, you need to start selling those.
Wine
People can
bottle,
measure
the
that.
wine bottle. It's a series of wine bottles, but I'm not. I think Jason, I can't see you, but I think you're here.
Here I am.
Thank you. And Jason really needs no introduction. If you haven't read his book, I'm not sure why you were here. I think that is probably the best way to introduce you, Jason. We're looking very much forward to your talk.
Can you see that? See this?
Yes.
Okay.
Yes.
Okay. Yeah, my sympathies to all those who have read my book. And I'm really sorry I can't be with you in person. That's a bummer, but those are the breaks. Let me also thank Chung Wai for the nice introduction, and also thank Ron very much for letting me talk again at his wonderful meeting, which is clearly going from strength to strength. So I'm going to talk about the physiologic components of impedance, ZRS. These are my disclosures. And the question I'm concerned with today is, what does respiratory impedance mean? And this is the question many of us ask all the time. Well, it reflects the mechanical properties of the respiratory system. We know that. And these properties include those of the lung, not exclusively, but we hope that the lung is a significant component of respiratory system impedance, and that in particular, when things change as a result of interventions, bronchodilators and so forth, that what we're seeing is the change in the lung. And ultimately, we'd like to link function, as embodied in a measurement of impedance, to structure, i.e. anatomy in the lung. And the question is, how can we do this? Well, the fact is, well, first of all, now the standard approach is an empirical one, and we've seen this many times before. We have parameters. R5 is conventionally considered to be total airway resistance. R20 is central airway resistance. R5 minus R20 is some measure of heterogeneity, whatever that means. X5 is elastance, and AX is basically elastance, and then we have the resonant frequency. Now, in order to put physiological meaning to those things, physiological interpretation, we have to use some kind of mathematical model. There's no alternative to this. Here's the simplest one we can consider. A balloon on a pipe. The balloon has a resistance R, an inertance I. I mean, the pipe and the balloon has an elastance E. That's what the impedance of this system looks like. It's this expression here on the end. Okay. Now, this model predicts that R5 and R20 are equal to each other, and they're both equal to R, the real part of impedance. That X5 is equal to that expression. The resonant frequency is equal to that expression, and I'm afraid to say AX is equal to that expression. That's what it is. You can work it out analytically. Now, AX, you can convince yourself is most likely to be sensitive to changes in E, but it's not just E. I can influence things as well. Okay, but that model is very simple. It can't predict frequency dependence of resistance, for example. So let's go for a fancier model. Two balloons on two pipes, central and proximal and distal airways and so forth with the compartments. And this is the model that I believe has influenced most thinking about oscillometry in the sort of clinical arena. That's what the impedance looks like. That's the impedance of that model. Okay, now, as I said, it predicts a frequency dependence, a negative frequency dependence of resistance. What is R5? Well, it's a mess. So is R20. X5, FRES, AX. And this is only two compartments. What if you wanted to have three, say a parallel and serial heterogeneity? Well, you can see where this is going. So I decided to take a different approach, and that is to try and build impedance up from the ground using a simulation model, or what you might call a virtual laboratory. And once you've set one of those up, you can do experiments with it. So I have what I call an anatomically accurate airway model. It's based on the Horsfield asymmetrically branching scheme, where airways are numbered from the periphery to the trachea as airway orders. Model parameters are the number of airway orders, which for a human is nominally 25, so the trachea is order 25. The Horsfield delta, the measure of asymmetry at each branching point, is 3. That's the difference in daughter order at any branch point. I'm assuming that the ratio of airway length to radius is a fixed number, 6, and there's histologic or anatomic data to support that. I'm assuming that as you go down in the airway tree distally, the dimensions get smaller by a fixed parameter, gamma. The tracheal radius is Rn is another parameter you have to specify. I also say that the trachea is longer proportional to the other airways, simply because it is, by a factor of 4. And we also have to assign a total elastance for the respiratory system, HRS. And since it's a constant phase model in the tissue, we have to have a hysterosymmetry parameter as well. We have the viscosity of air, the density of air. So the basic lung model, just the airways and the parenchyma, is what I just said. I'm going to assume N is 25, delta is 3. I'm going to give it a total lung elastance of 50, a tracheal radius of 1 centimeter, which is sort of in the middle of the average range for males and female adults. The airway scaling factor, the fraction by which they get smaller as you go distally, is 0.88. The airway length radius is 6. Ratio is 6. Actually, that should be 4. It's not 3. And I assume Poisson flow in all airway branches. And the reason for that is there's a mathematical formula that enables you to calculate the resistance of every branch. And once you've done that, you can add all those resistances up in series and parallel, as the case may be, and calculate the impedance of the entire model. And when I do that, what I'm showing here in the black are data collected by my colleagues at the University of Vermont in a group of normal adult humans, normal lean adult humans. And so you can see the black circles are the resistance and the black open circles is the reactance. And using the parameters that I just said in the previous slide, the red shows the prediction of the model. Well, the prediction of reactance is pretty good. See that? But the prediction of resistance is really terrible. It's way too low. So what can we do about that? We're clearly missing something. Well, one thing we haven't done is accounted for turbulence in the airways. We've assumed just purely laminar Poisson flow. A famous paper by Pedley et al. In 1970 came up with a prediction that as you look at the proximal airways, they increase in resistance by various factors depending on the flow rate, according to the presence of turbulence, high Reynolds numbers in those airways. And I sort of came up with an empirical way of describing the average effect there, which is an exponentially decreasing correction factor as you go distally. When I put that into this model, the reactance still is a good match. The resistance by the models increased a bit, but it's still nowhere near it needs to be. So what else do we need? Well, we have to include the upper airways. The upper airways, and when in doing this, I found I had to drop the lung elastance a little bit to get a good fit. I'm assuming equipment and upper airway resistance of 2 centimeters of water times seconds per liter. There's a proximal gas inertance because if you have any kind of a conduit, there's an inertance there. The shunt elastance, this is the elastance of the gas and the cheeks and the pharynx and all that kind of stuff in the upper airways. That's been reported to be somewhere between 600 and 2,000 centimeters of water per liter. I chose a middle value of 1,500, but there's a lot of play there. When I do that, I get a pretty good match. Although it's not perfect, you'll notice the simulations are starting to have a positive dependence on frequency, and it's heading towards what I think is an anti-resonance around about 35 hertz. Okay, now a critical thing. So far, I've not included any stiffness or elasticity of the airways. And if you're going to have any parameter that tells you central versus proximal airways, there must be a finite stiffness of the airways. The airways must act like a compartment. How do you put that in? Well, I assumed the specific elastance of the terminal airways was the same as the parenchyma, since they're very thin. I assumed this specific elastance increased linearly with order number up to the trachea, so the trachea is the stiffest. And by choosing a specific elastance for the trachea of 200, I got a total airway elastance of 500 centimeters of water per liter, which is what Mead, back in a famous paper in '69, on sort of bulk measurements decided was a reasonable value for airway elastance. When I put that in, it increases the positive dependence of and resistance on frequency, and does a weird thing here. It brings the anti-resonance to a lower frequency. We're beginning to see the effects here. So it's not perfect, but it's not too bad. Now the question is, let's put in bronchoconstriction. So there's two ways to do that. I can either reduce all the radii by a given fraction, or I can keep the trachea the same diameter, and I can bronchoconstrict increasingly going down distally. And that's by changing the scale factor from 0.88 to 0.84, the thing called gamma. When I do that, the black is the human data. The red and the blue are the simulations. The red in the case is just decreasing all the airways by a factor of 0.5, and the blue is progressively increasing the constriction of the airways as you go distally. And you get similar effects. You can see it introduces a negative dependence of resistance on frequency. And these are purely arbitrary choices, but it has a similar kind of effect. And there's no resonant frequency note. So what does R5 minus R20 mean? Well, it could either be due to upper airway shunting, or it could be due to airway wall compliance, or both. If I look at these individually, upper airways only in the model, so I only had upper airway compliance, I get the red. If I have airway wall compliance only, and this is in the presence of bronchoconstriction, airway wall compliance only, I get the blue. So they do similar things, and if you put them together, you're going to get an increased effect. So the conclusions are that the clinical use of oscillometry is currently based on the empirical parameters R5 and so forth, and I'm not knocking that. These are very useful biomarkers. It's quite clear everybody is using them with increasing success to characterize all sorts of disease conditions and follow the progress of treatment and so forth. But when you ask the difficult question of what do they mean physiologically, you have to start invoking computational models, and that's where it gets a little tricky. If you build impedance up piece by piece, you predict measurements reasonably well, but there's a model ambiguity problem because that R5 minus R20 could reflect upper airway shunting. It could reflect shunting into the airway wall compliance itself. It's most likely both in indeterminate proportions. And also, when you bronchoconstrict, it's pretty clear, it's kind of obvious, and it's also been demonstrated that the stiffness of the airways increases. So the airway stiffness I used in this model is going to be too small for a bronchoconstriction case. What it should be, I don't know. But anyway, I will leave it there and entertain any questions. This is a work in progress, you might say.
Thank you very much. Zoli has his hand up.
To second congratulations, Jane, and fast recovery. And I just at least one point. It's very pertinent that you stress the central airway whole shunting, including the cheeks or starting with the cheeks. So it's very, very important. What we measure is not lung impedance, it's total respiratory impedance. So chest wall is added all the times. Chest wall impedance is not time independent because the picture of the respiratory muscles is peaking. That's one point. I agree on emphasizing all these things, but in bronchoconstriction, it's not clear for me. How do we count the potential inhomogeneous response of the different parallel compartments? I go back to the Otis model.
Yeah. Well, you know, in the interest of time, I didn't get into that, but I can do that with this model as well, because just a slight, technical note is I calculate the impedance using a recursive subroutine that calls itself over and over again, working its way down the lung and back up again. It's, you know, Ken Luchin and Bela Suki have used similar kind of approaches. And it's really nice because you have really pretty short computer code that will calculate the impedance of the entire lung. And the software keeps track of all that stuff. But as you do it, when you're calculating the resistance of the next airway branch, rather than using deterministic values for resistance and length, you can draw a random number from an appropriate distribution and make it stochastic. So in that way, you can build in any degree of parallel heterogeneity you want. And I played around with this, and if you do that, you can also reproduce a lot of these negative frequency dependence effects. You know, it gets back to the age-old dichotomy between the Otis model and the Mead model, and which is it? And it's probably both. And, you know, so this is where, you know, I'm interested in trying to link structure to function as close as I can using these models. But there comes a point where you just run up against ambiguities that you can't resolve. So in the end of the day, for clinical practice purposes, you come back to these empirical parameters, which are very useful. But when people say, I guess the cautionary tale here is when people say that R5 is total resistance and R20 is peripheral resistance. I don't know. Really? You know?
Charlie.
Jason, is always really nice, your presentation. In adjusting the models so that it fits better, because the resistance you first found out was kind of low, and then you added some different things that central airways resistance. I was wondering about bronchoconstriction that's due to neural tone. So the Horsfield model is based on assumed data, which is all done in cadavers that are dead lungs that have been fixed in formaldehyde and don't have the parasympathetic tone that all our airways have. And I was wondering if you had thought about adjusting the model using something like that.
Well, it's a good point. I mean, that would be the Horsfield model is a branching structure, so that's not going to change whether you're dead or
No,
alive.
that's not going to change. But
What might change is the diameters and lengths of the airways.
That's
So I put in nominal values that are supported by anatomic data in the literature, but yes, they are always open to question. The other thing is that the Poisson flow assumption in the airways is way too facile. It's the Reynolds numbers in the upper airways and the fact that they're very short and you don't have steady flow and all those fluid dynamic effects means that the resistance is actual flow resistance is going to be higher than that you would predict from those measurements. So it's a question of guessing how much. But just a practical point going forward, I mean, I think it's possible, in principle, first of all, to measure all the equipment resistance and take that out of your measurements. Then possibly, if you could make impedance measurements with the closed glottis, you might be able to estimate the upper airway impedance and take that out. So we could get closer by doing the appropriate calibration maneuvers to what the actual lung impedance is, but something to think about.
Well, I think in the interest of time, Ron giving me the evil eye, we'll move forward. Thank you very much, Jason. Our next speaker is Jeff Maxim from Dalhousie, and for some of you may not know, but Jeff is an alumni of the Bates Lab, so it's a very fitting.
Where? Oh, you chair.
Yeah. Thank you very much, Chung Wei, and thank you very much, Ron, for inviting us again and for a wonderful seminar series for the 10th time. So I'm from Dalhousie. That's a picture of Dalhousie. And yes, I am a trainee of Jason, so it's quite fitting that I think I'm following him. So what am I talking about? Reactance inversion. Reactance inversion is variously defined as something where the reactance is actually doing something strange at the bottom. When I have a normal human lung, we don't expect to see reactance moving upwards like this. So reactance inversion is actually a downward trend, and then finally what we expect to see an upward trend over here. And in this particular study, this is a 6-year-old boy with CF before and after discharge up and bottom, and the inversion is still there. And it's repeatedly there. Not all the time. Sometimes the traces are going down, sometimes the traces are going up. And resistance is, I'll also point you to the fact that down around 5 Hertz, it's also moving when X5 is moving up and down. So what could that be? We see that it does happen. It happens. This is a study in 2021 in asthma, and they talked about observing reactance inversion in impulse oscillometry. And so how often did it occur? It occurred, they called it CX5, so the inversion. They saw it in various degrees. 64.8% of children actually had it, and it was distributed differently. So this, I don't think that means that their mean values always 64.8 had this artifact. I think they saw in repeated values that occasionally it had the artifact, right? So they're counting it like that. They speculated in that paper that this artifact or this behavior was either a Helmholtz resonator, which I won't bother to explain, but it's essentially a kind of shunting thing, which has a resonant frequency ahead of the respiratory system, a low frequency leak, so some leak in the system, parallel pathway differences in time constants, so something important physiologically. I disagree with that. I don't think that's possible. Parallel high impedance path, so they really didn't know my message. So I'm going to go straight to some data that we had. How often did we see it? And data that we collected in the child cohort. So this is a population-based study, multi-city in Canada, all measured with the tremoflow. And so the number of measurements that actually had an X inversion, so that X was at 5 Hertz was bigger than at, in this case, 11 Hertz, was up close to 9%. And this is actually the mean value. So 10% of the people had their mean values actually showing that inversion. Another study, this is also with PJ, sorry, this is with PJ Savara University at Toronto, called the Wheezy study. So it was children who presented with wheeze and a younger group. And we see that the number of people, of children or subjects that actually presented with X5 greater than 11 is larger, 22% of them. So that's a significant population that are showing this effect.
So if I do it like any test, so in this particular study, PJ did not just 3 measurements, but sometimes as much as 8 to try to get the the coefficient of variation to the acceptable levels so that they had reproducible measurements. But since we had all those measurements, we could see that occasionally it occurred a lot, 73% of the time, right? But you would eliminate those values that were abnormal and keep the ones that were consistent as much as you can using the coefficient of variation. Okay, so what do I think it might be other than the mechanisms that have been proposed in the literature? So I went to an obvious one. Well, breathing is the most challenging noise that we have in oscillometry, and it's worse in breathing. And in fact, modern measurements of oscillometry say we shouldn't be doing 5 hertz anymore. We should do 7 hertz to stay away from the breathing noise, right? To try to minimize artifacts of any type. But this particular artifact, how does it actually come from breathing? That was the question that I tried to ask. So this might be the breathing signal of a child or an adult, I guess, because it's pretty slow, 0.2 hertz. And there's a lot of bumps and wiggles and this sort of thing. I'm calling it harmonics, but really it's just the noise from a complicated breathing waveform that has multiple frequencies that extend all the way up to 5 hertz, all the way past 5 hertz. It's just getting smaller and smaller and smaller. Some of it is at 5 hertz, a very small amount, hopefully. So I created a model. So this is the words that describe the model. So I used the single compartment model, which just has a resistance, elastance, and inertance. And I would put some noise at 5 hertz that has to come from breathing. So I would vary the amount of noise according to a parameter I called alpha, so the alpha harmonic, and I would give it a phase, a theta. That just means if I'm looking at the spectrum, a spectrum is all the sinusoidal components of whatever the waveform is. So the breathing can be a complicated waveform, but at 5 hertz, it's always going to be a sinusoid. So, I mean, that's the definition of a component at a frequency. It's a sinusoid. So all I need is an amplitude and a phase. I generate a normal oscillometry signal, like from the TremorFlow or the Resmon or any device, and I have a breathing signal. I don't need the complicated waveform that actually exists as breathing. All I need is the component that's going to hit 5 hertz because I'm going to measure 5 hertz. So I use my breathing noise. So whatever the sinusoidal component is at the breathing frequency, see, it's omega B, so it might be 0.1 hertz or some other frequency. But I'm going to add a harmonic that occurs at 5, right? And I'm going to reduce that strength of it or increase that strength of that harmonic by this coefficient alpha. I will compute the pressure that's measured using the model. So the patient will have, or the subject will have a resistance that I define, an elastance and inertance I defined. Then I will add this VB, which is my breathing noise, which actually won't matter, but the harmonic will. And I'll also compute a pressure. And then I'll compute the ZRS by our usual method, which is known as the cross-spectrum analysis. Essentially, it's pressure divided by flow in the frequency domain, but in a spectral formula I'm not going to get into. So I did 2 models. I did a bunch of models, but here you're going to see 2. So the healthy subject, the model is a constant resistance across frequency. And so that's what I put in. And I'm only going to be interested in 5 hertz, but I'm showing you what the patient has. Right, and the reactance for this patient I defined as pretty close to 0, minus 0.6. Right, that actually I defined the reactance, and that in turn gave me an elastance and inertance according to the model. And so the not healthy person has a resistance of 10 and a minus 5. Those are numbers you might see. You see them more often in children than you will see in adults. I don't really care if it's a child or an adult. This is just the impedance. And this would be the E and the I that would have to correspond to this model, whether it be choosing these 2 parameters. Okay. So now I'm going to add a harmonic strength of 0.005. That means the fundamental breathing signal is a typical amplitude. So it's breathing of a half a liter, or I forget exactly what I put in, but it's a typical breathing signal that you might measure from an adult, actually. And then the harmonic strength at 5 hertz is 0.00005 of that. Very, very small. We should expect nothing because that's tiny. really big, tiny. And I varied the phase of it. And so there's actually 16 measurements. Nothing happens, right? So R5 and X5 are very negligibly altered. At this strength, no X inversion. The not healthy subject, something started. So the resistance is actually starting to move around 10 at 5 hertz, nothing happening at the other ones, right? And then at X5, something happening, but no X inversion as defined by X5 being higher than X10, or 11 in this case. Healthy subject, I'm moving it up. I moved it up by an order of magnitude. Still pretty tiny relative to the breathing strength, right? Again, 16 phases, negligibly altered, no X inversion. Now the scale is kind of blowed up or like expanded because I'm getting to where I'm going to do the non-healthy subject. I'm going to fill the screen soon. But no X inversion. That means X5 is not higher than X11. Now the not healthy subject, I move it up again. If I didn't do the number, it is moved up again. And at some phases, things are looking okay. At other phases, I do start to see X inversion. So just a few of those phases, it's higher than X11. But you look at that, I actually have a patient who didn't have had an X5 at -5. So this number is the correct one. Look at all these wrong numbers. Just by that small bit of breathing noise in that frequency. Now, that's surprising, but because I'm defining a very narrow thing, and there's another secret in behind this, is I'm not making the breathing harmonic change during breathing. A person isn't going to breathe exactly the same every single cycle. So I'm actually doing a very bad choice, right? So probably I'd need to do something a bit larger if I was going to do non-coherent breathing, but I didn't model that. I'm just putting in a certain strength. Now, even if it was non-coherent modeling, the strength of the coherent component of that would still be something valid. So let's consider that this is the coherent portion of a non-coherent noise. So it is small. But there's a narrow range where X inversion is occurring. Now I move it up to something larger. It's still a small number. I don't know if this is physiologically or realistic, but when we look at some data, which is coming up, you might think it could be. But I do have X inversions. I have X inversions that are going positive, and sometimes that even happens. So in this non-healthy subject. So the correct number should be this one at -5, and all the other numbers are wrong. Right? I'm going to some crazy negative numbers. The disturbing thing is when this is happening, it has to happen to resistance too. Right? So we're actually used to seeing R5s go high and come down. But what if it was actually noise? This artifact I'm talking about could happen. But the symptom is probably inconsistency. So if you have R5s that are positive, negative from measurement to measurement, because here, these are all different phases. And when I start the oscillometry, what phase is my breathing? We don't actually time it, right? So it's random. So the different phases are probably realistic. I don't know what the ranges might actually be. Okay, so the real contamination would be very breath to breath, varying with amplitude and phase. It should be more common in faster breathing because all that noise at the low frequency 0.2 from breathing, if I breathe suddenly at higher frequency, it should move it up. And there's another thing I want to introduce. It should be more common in square wave breathing because harmonics from a signal sinusoidal breathing, that's actually a leading thing. There aren't any harmonics from sinusoidal breathing. There's just one, it's the base fundamental. But if I have a different waveform that's more triangle, I'll have harmonics that go up until high frequencies, but they drop off really fast. The square wave is the worst one. If I breathe with a flow that's on and then off, well, actually inhalation at a constant flow and exhalation at a constant flow, people don't actually breathe like that, but some people are close to that. You look at the flow traces, it goes up and down. Those ones have the worst possibility for a given amplitude of having a harmonic at 5 hertz. So those are the two things that might actually predict this behavior. Okay, so I did different phases. What phase is actually the bad phase to show X inversion that we see? So here's harmonic strength 0.001. These are the different phases I tried. Remember, 5 is the correct answer. A phase of 0, that means in phase with flow, I think. No, in phase with respect to volume in this graph. If it's 180 degrees out of phase with flow, that's actually where we start to see X going positive. Just for those who are interested. I'll skip that. I'm going to show you. So I asked Thorasis to actually look at this, and Leonard here and his team actually tried to do breathing at different respiratory rates, and they tried to do breathing that was more square versus less square, looking at the screen and that sort of thing. And just a couple of days ago, we looked at some of the results, and I had decided, oh, those are cool. I'm going to include them in the talk. So here's a single subject doing respiratory rate of 20 breaths per minute. Look at the 5 Hertz component. It's pretty consistent, and everything looks good. Okay. Now look at 40 breaths per minute. There's actually a slight spread happening, right, in this subject. Now look at the 60 breaths per minute. There's a bigger spread. We have one curve here and that curve. We don't have X inversion per se. We don't have X5 going up, but we see a spreading. So there is an effect. They tried to breathe the same in this particular case, and they just sped up their breathing. I think I also tried to do square wave breathing as well as they could in this particular one. So it's not so square. This is flow in this run, this is volume, and it's not square. As we go closer, it gets more square. This is 60 breaths per minute, and you can see flow is high, flow is low, flow or positive, negative, positive, negative. And that's where we see the spread. Here's a patient from a larger study, one patient where X inversion is actually present, and you can see that from different recordings, it's up and it's down. If I looked at the trace, the respiratory trace from the case where X inversion actually occurred in this subject, this is the actual trace. It's incredibly square.
It's actually not a child.
It's not a child. Oh,
No, there's an average woman. She's like 29.
Okay.
Yep.
All right. Sorry.
That's
That's pretty young compared to me. All right.
I agree.
All right. So not a child. So potentially, this is a mechanism that could be responsible for X inversion. So I'll draw this to a close. And I'm going to acknowledge there's a picture here. I was very fortunate to be invited by Rafael Deleca for a course, a summer program in modeling, oscillometry, respiratory mechanics, and imaging. And we had to give the students who are there special projects. And so during that time, I said, oh, I have a special project. I asked the students to see if they could put a leak in their antibacterial filter and see if they could reproduce, trying to do intermittent leak and leak with different amplitudes, different styles of breathing, and they couldn't do it. I don't actually have the data. Well, here it is. It's on the screen on this picture, but they never found X inversion that way. I need to do it more systematically, not like that, which is very fun, but I need to do it in a less fun way. But it's still possible that an intermittent leak at exactly the wrong phase might possibly produce this as well. I actually think it's more likely that it's just normal breathing noise, and we see it at higher events when the breathing noise is greater than silver and with higher respiratory rates. And we see it with more square wave breathing, although I have to quantify that. If this is true, though, or I forgot to say, there's also contamination of R5. So if that's the case, I'd actually like to get rid of this, right? Because R5 is very important. X5 is very important. Can it be mitigated or removed? One way is to increase the lowest frequency in subjects where this is more common. That we're already doing. We're recommending using 7 Hertz as the lowest frequency. And if we go, if the noise is coming from a fundamental at 1 Hertz, which is pretty high for breathing, maybe it's 0.66 of a Hertz, you can compute, it's basically a 1/F characteristic with frequency if it's a square wave. If it's a triangle wave, it's even faster. So it's probably pretty fast. The decrease going from 5 to 7 will be, at least 2 or 3 harmonics, maybe 5 or 6, depending on what the fundamental frequency is. So there should be a dramatic improvement or some improvement if we do that. We could also change how we actually instruct the patients. What we would like them to do is no harmonics, breathe like a sine wave, sinusoidal in, sinusoidal out, and there'd be nothing, no problem. They're probably not likely to do that, but maybe if we looked at the square waviness and just said, let's try that again. Why don't you breathe a little more easily? Or some instruction that we would actually find out that still we're measuring the mechanics, because we don't care about breathing. We care about the resistance and the reactance from the oscillations. Could we detect the square wave breathing and maybe eliminate those times it occurs, or again, instruct the patient? Or are there other signal analysis modifications that we did? I did mention that we're using the cross-spectral analysis, which means we're taking 1 second chunks and doing averaging. That means our bandwidth at 1 second for accepting noise is actually fairly big, 1 hertz. If we instead did a frequencies, a Fourier transform of the whole thing, our bandwidth gets very tiny, and the leak from breathing might actually be smaller. I'd have to test that. But there's a possibility of exploring a signal analysis. Anyway, with that, I'd like to thank my collaborators, which Guadalupe and Leonard at Thoracis, Anas, who was my student and now at Thoracis, and clinician who I talk with a lot. So, thank you very much.
This is actually a really important topic, so Sam, if that's okay, we'll take a couple of minutes. But maybe if I could just ask first, for those of you who actually have large data sets, how often, because I'm stunned by 22%. How often do you see this? Because I know that in our data set, we have about 40,000 tests. We've only seen a handful. And so I want, for those of you who've got large data sets out there, because it scares me that we're going to get rid of our hertz. But no responses. So there's only first. Yeah.
I do. I see it quite a lot, but the 20% in pediatrics and young children 8 to 6 years old, almost at least one test probably has it. They're first getting used to like using the device. So I see it 20%.
In children. Kids, and I see it. I nod. Do you also see
quite a lot in children?
Yeah.
And we use it as a marker of severe obstructive disease in children. So actually, it's useful for us if you see that.
But I would argue that it's not that long. It's just breathing noise.
Okay.
Yeah. So it's just artifact. Not.
It could be. That's my hypothesis.
Has anyone tried to have this and then give them, let's say, a metronome and have them go?
Yeah, because I'm from Toronto, and I actually asked him a couple of months ago and said, I'm seeing a lot of I'm seeing preschool. And so he told me, like, try to ask them to breathe like slower. So then only one patient, I would say that he actually improved that, but it was only one. And I've seen like very frequently. And they didn't understand how to change the square.
Probably.
Slowly and Charlie.
I'm a.
Jumai?
Slowly first.
So I would refuse the suggestion that we change the subject's breathing pattern. We have to change the performance of the device. So that's in pediatrics. It's not very practical. This phenomenon is device dependent. There are manufacturers who correct for this error, which is totally intolerable, I think. And a third remark, there, in addition to the breathing as another flow source to the oscillator for flow, there's a third component, third generator behind the heart.
Yes.
Jason has had a very nice study, but this intertrachea pressure fluctuation at the heart rate were utilized to assess pulmonary impedance.
I've done that.
And
it works.
And just to make it clear, if you make measurements, then the spectrum shows this cardiac, and it's very, very high harmonies. They are in between the breathing signal and the oscillator signal. So they are a major component.
Yeah. Actually, if I could just follow up on that.
Jason, yes.
Yeah, that's a great point, Zoltan. I was wondering about the heart rate. But Jeff, this is a terrific study. You may have solved what's been a conundrum for quite a while. Just one question I had. When you do the analysis, you have to filter out the breathing waveform somehow, even if it's just linear trend subtraction over the little epochs that you're using.
Yep.
And that's never perfect. Do you think there's any way in which artifacts or stray components of frequency could be left over from doing that?
We do filter out the breathing component, but it's usually at some frequency like 2.5 hertz or something like that below the 5 hertz component, or at 2 hertz or something like that. So the noise that's contaminating 5 hertz is still there and largely unaffected. If the filter is a poor filter, but the filters that I use are phase invariant, and they take away all the noise below 2 hertz to a very small amount.
But what's their roll-off rate? I mean, no filter's perfect in that regard.
Well, I actually use, because it's a model, I use the Fourier transform. So I actually make it 0.
Oh, I see. Okay.
So I erase all the components from breathing above, sort of below 2 hertz.
Okay.
So they're not no effect. But that's not what the field does. The field does something else. So it's more, it's better to use, and they use anything from a 4-pole Bessel to a 2-pole or a 4-pole Butterworth or something like that.
Yeah. Okay. All right. Thanks. Great work.
I have to sit down.
Thank you. So we are 6 minutes over time. So I'd like to welcome Sam Bayat from Grenoble, and thank you very much for coming. And it's going to be a shift in our topics. He's going to be talking about transfer emissions chest imaging.
Yeah, thank you very much, Chung Wei, for the introduction, and thank you, Ron, for letting me speak, and the co-authors, and thanks for organizing this wonderful seminar that I've been following over the years remotely, but I'm really happy to be here for the 10th edition. So, yeah, so I guess I can start right here. Yeah, so today I'll be speaking about transfer admittance chest imaging. Here are my competing interests. So the study was funded by Austral Diagnostics. So as you all know, respiratory diseases cause mechanical heterogeneity in the lung, and we all know that spirometry is less sensitive than oscillometry to detect that. And oscillometry tends to be slightly more sensitive, but it gives a global measurement. You don't get spatial information from oscillometry. And there have been tentatives to use imaging, such as MR elastography or laser vibrometry, to sort of map the spatial differences in the mechanics. But these techniques are costly, point-wise, or they need shielding, so they're not practical to do at bedside. So we need a bedside radiation-free method that allows to map regional lung and chest wall function. So conventional oscillometry measures input impedance, where the oscillatory signal is pressure is applied at the mouth and the flow is measured at the mouth. Now, if you apply the pressure at the mouth and sense the flow or the volume changes at the far end of the respiratory system, which is at the chest wall, then you get transfer impedance, which is the ratio of input pressure to output flow in the frequency domain. So historically, this transfer impedance has been measured using I don't know if you can see my, yeah. It's been measured using body plethysmography, where you can apply the oscillatory signal at the mouth, and you can measure the chest wall flow, in a sense, or volume changes as a function of time with the body box. And you can do it the opposite way. You can apply the pressure at the chest wall and measure the flow at the mouth, and these give equivalent measures of transfer impedance. Now, there's a seminal study by the Milano group, Andrea Liberti and Raffaele Dell'Acca, who's here, and they proposed for the first time a technique using optoelectronic plethysmography, and that involves putting these markers on the chest wall and the abdominal wall, and they image the chest and abdomen using optical cameras, and using some post-processing, you can get volume changes as a function of time. And if you apply the pressure signal at the mouth, then you could get regional, for the first time, regional data on the mechanics, on the transfer impedance. And so you can get different parts of the chest wall, the pulmonary, the abdominal chest wall, and the abdomen. Now, the concept I'll be speaking about today is slightly different in that Austral Diagnostics made this technology that it's an antenna that is an array of ultrasound emitters and microphones. And so initially it was designed to actually look at cardiac activity on one hand, and on the other hand, to look at the respiratory activity using vocal fremetis. But the issue is that vocal fremetis is very challenging because you can't standardize it. I mean, in terms of frequency and amplitude. And many years ago, I'd done this experiment with using an ad hoc setup that was built by Zoltan Hantosh's lab, and it's a wave tube system with one of the founders of Austral Diagnostics, with Ross Ing. And what we did is that he had a laser interferometer, and we used Zoli's system with the laser interferometer on the chest on a healthy volunteer, of course, and that worked pretty well to measure transfer impedance. However, a laser is a point-wise measurement, so to raster scan the chest, it takes a very long time, so we sort of dropped the idea. Now, with this new technology, we use a Respond Pro to apply the pressure signal at the mouth, and it also provides the pressure signal and the laser, basically the ultrasound, they call it AUSMC, which is Airborne Ultrasound Surface Motion Camera. So it images the chest, and what it does is it can detect minute vibrations at the chest. So you get a velocity field. And if you basically divide the velocity field by the pressure in the frequency domain, again, you get local admittance. So if you integrate this over the region of interest, then you get an admittance map, and so you can get both the amplitude or the modulus, and the timing or the phase. So you get two maps actually. So the grid is about 30 by 40 centimeters square with a resolution of 3 centimeters square. Now, why admittance? And this is let's say a practical thing, is that in this configuration where you have a single input, multiple outputs, admittances are additive. So you can integrate them over the ROI. And of course, afterwards, you can convert them to impedance. So admittance is the reciprocal of impedance. So the study that the data actually were acquired in 6 controls and 6 age and sex matched COPD subjects. So this is part of a sub-study of a clinical trial that's ongoing. And the subjects were upright. They were sitting, the dorsal side of the chest is imaged. They had a nose clip, supported cheeks, and filtered mouthpiece. So this is compliant with the recommendations, of course. And so we do a 1-minute pseudorandom measurement, and then the chest imaging acquisition is only 10 seconds, which is a couple of breathing cycles. And it's quite short. Now, here are the initial results in a normal subject, representative normal subject on the left-hand side, and a COPD subject here. Each subject has an amplitude map of the admittance and a phase map. And it appears that, as you can see, the normal subject has the chest lights up at all the frequencies and all pressure signals, while the COPD subject, it's dark. The chest images are dark, and for the same pressure signal, you get very little admittance amplitude. And the other point is that the phase polarity transition, you see a polarity transition in the phase. Basically, the phase changes signs, and this occurs around mid frequencies in the normal subject. It becomes negative, while in the COPD subject, this moves to higher frequencies, which is rather an expected result. So now you see the same result where the median IQR over the 6 subjects. In green, you see the controls, and in orange, you see the COPDs, and you see how these are significantly different. You see the modulus, or the amplitude, on the top graph, and you see the phase at the bottom graph. And the phase actually showed stronger significance in differentiating the COPD and normal subject. Now, if you convert this to impedance, because we're more used to seeing impedance data, so on the top graphs show the transfer impedance. The bottom graph shows the input impedance, because you use the Resmont Pro, so you also have the input impedance. And first of all, these show typical, let's say, aspects of input impedance, whereas in the normal subject, the resistance is quite flat as a function of frequency, while the transfer impedance in the normal subject, that's a green curve, it sort of decreases with frequency. So that's consistent with known data. The other point is that the actual transfer resistance, the value is about 10 times the input resistance, and that's also to some extent an expected value, because we're looking at a small R1. Well, actually, we're looking at a region of interest, so we're downsampling the actual flow, and also the dorsal side of the chest moves less than the ventral side. So to some extent, that is an expected result. The other point is that if you look at the transfer impedance, it's mainly the transfer resistance that distinguishes the normal and COPD, while in the input impedance, input resistance is, you see some frequency dependence in the COPD subjects, but it's mainly the reactance that distinguishes the two groups. The technique has strengths. There are some potential clinical avenues and some limitations. Strengths are that it's contactless, radiation-free. You can do it at bedside. It gives a wide field spatial map of the mechanics, and you can get your input impedance for free as well. And there are no markers, and slightly higher spatial resolution as the OEP technique. At the moment, the clinical avenues are hypothetical, so there's no data on how it can be used. Is it a potential complement to spirometry and oscillometry? I mean, definitely the fact that it could give some spatial data is potentially valuable. So I'm particularly enthusiastic about that. But I think what we need to do is to compare this with imaging techniques, the CT, to see if we're able to pick up emphysema, condensation, parenchymal inhomogeneity, in a sense. So that if that evidence shows up, then I think that would be even more exciting. So again, there are limitations, but there's also room for improvement. For the moment, the technique looks at the dorsal ROI only, but you could imagine having an antenna that does a 360 degrees. It's just a matter of cost, because I think the components, they cost a lot of money. For the moment, only the whole breath is exploited, but actually the maps that I showed you, these are movies. That's why it takes a lot of memory, because you can follow the admittance over the entire breath. So we haven't looked at the inspiratory, expiratory changes, and I think that's a big potential there. For the moment, also, you only look at the chest velocity, which is aligned to the beam of the ultrasound. You don't look at the out of surface component. I think that, again, that's extra data that could be potentially important with shear waves. And also, yeah, the limitations due to the fact that it's a small study with only 6 subjects. So in the meantime, the study was published. You can look it up. And there's an ongoing clinical study that is led by Thomas Emilovsky, and it's in Caen in France. We're looking at cardiac patients and respiratory patients with various diagnostics. There's some preliminary data on medRxiv. And with that, I'd like to acknowledge the colleagues. Frederick Rinsenrath and Mathieu Quad are the 2 engineers at Ostra who did the heavy lifting. Colleagues from Caen and Moadil and Salou are physicians from Caen. And also the founders of Ostra are Matthias Fink, who's a famous physicist, Ross Ing, my colleague engineer, and Thomas Emilovsky, who some of you may know. Thank you very much. Ron.
So, some of you know, Thomas was a contemporary chef to myself at Vegans back in the day. Could you go back to the slide of your map showing the decibels and phase shifting? If I read this correctly, have you shown us that the often misguided statement that the reason there's a frequency dependence of resistance is because low frequencies go further than high frequencies? You show the opposite here, that in the healthy got an equal penetrance of all frequencies as expressed by the heat map.
Well, it's hard to say based on this preliminary data, I think, because, first of all, keep in mind that we're looking at admittance. So it's the opposite we're looking at. Is there some frequency dependence? I think it's easier to see that on the curves over here. And the transfer impedance behaves differently than the input. The transfer tends to decrease with frequency, so it's a whole new set of data. Again, yeah.
Better luck next time.
Question?
Yeah.
Can I ask a question?
Yeah.
Yeah. Hey, Sam, very elegant work, and super sophisticated and everything. And from a scientific point of view, this is really interesting because it enables you to potentially look at heterogeneity and this kind of thing. But I'm just trying to think of what the ultimate clinical application might be. And I wonder if you've thought about that. Like, for example, could you look at a COPD and find out which part of their lung is not ventilating, and then maybe that becomes a target for volume reduction or something? What do you think?
Well, that's completely the idea. And even, without looking at COPD patients who have a established disease, the thinking of the initially was to put this in the ER, and people come in there with respiratory distress, and you check out the mechanics, and you also see that one side is not, not good, basically. So that's one aspect. And the other aspect is that already in the clinical trial, and I didn't show those data, but you can look them up. The idea is that you can also use statistical models to link the patterns with disease diagnoses or physiological conditions. I think there's potential there. I really think that there's also data, that may not be really perceived or not be easy to pick up visually, or that maybe there statistically that you can link to disease. But I think that the next step logically would be exactly like you say, to compare this with imaging to see, can we pick up regional changes? That would be really nice.
Yeah, actually, it seems like something that deep learning might, machine learning might be applicable to.
Yeah, absolutely.
Yeah.
So that's a subject of the clinical trial.
Okay. Right. Thank you.
Yeah, wonderful. Have you thought about throwing an EIT belt on there at the same time?
Yeah, very good thought. And I think that it hasn't been done with EIT, but it's been done with impedance plethysmography, with chest bands and abdominal bands. Transfer impedance has been measured that way.
I was just in terms with the imaging that you're
But
doing.
EIT, the cool thing is that, okay, we did try that.
Yeah.
So, but we did try doing that, and it is challenging because you have to synchronize the EIT with the pressure signal, and it's a whole can of worms. There's actually a paper, a very nice paper on that. Another group that did the EIT, and what's nice about the EIT is that you can get regional impedances for. So theoretically, it's possible, and I think actually there's a small study that shows it possible. Practically, it's difficult to do technically, and the fact that EIT, you have to put the belts, you know, you have the electrodes, you know, you have to fiddle with them to make sure they all work, etc. The cool thing with the antenna is that there's no contact. You just sit in front of it and get your image.
Maybe a sort of a naive question, but would it be able to differentiate between the sort of fusion versus consolidation or the segment lobe that's not being ventilated? Or pneumothorax. Or a pneumothorax, although you should be able to pick that one up.
It better pick it up. Yeah,
Would it be able to differentiate? Because that I can see that as being very, very useful bedside test for patients who are very sick and are not, you know, where transportation to a CT scanner is.
Absolutely, I think that is one of the avenues where you can potentially apply it. Perfusion patients are not included in the clinical study, ongoing one, but there's a study in preparation in the ER, and we'll see what comes up.
Thank you very much.
Thank you.
I think I will also take this opportunity to thank the audience for your questions, because that it's the questions that really drive the discussions and our excitement with the seminar. And we will be reconvening at 1 o'clock here on the dot. I'm talking, but I don't know where lunch is, so I'm gonna let Ron give us this.
Okay, so lunch is served on the 6th floor in the lobby area. So go up there, there'll be sandwiches and drinks and a whole lot less packaging this year than other years. And a shout out to industry who's been helping us not only fund it, but also with the logistics of lunch. And I think it was Thoris's legwork that transported the sandwiches here. So advanced thanks. And yeah, let's be here 1 o'clock, and we'll start on time and keep on time so we get to the networking supper on time.